What if everything you thought you knew about the cosmos was just the surface of a reality so much stranger and more wonderful than you ever dreamed? We look up at a night sky filled with familiar stars and constellations, feeling like we understand the basic rules of the universe. But what if those rules are merely suggestions whispered in a cosmic language we are only just beginning to decipher? The universe is not the cold, empty void it sometimes appears to be. It is a living, breathing tapestry of mysteries, each thread woven with truths that defy our everyday logic and challenge the very foundations of what we consider real. It's a place where common sense breaks down and the impossible becomes not just possible but commonplace, inviting us on a journey far beyond the edges of our current understanding. This video is your ticket to that journey, a curated expedition through 30 of the most surprising truths the cosmos has to offer. We are going to venture from the impossibly small, where the fabric of space and time itself churns in a quantum foam, to the unimaginably vast, where the edges of our observable universe mark a horizon beyond which we may never see. Each of these truths is a piece of a grand puzzle, a revelation that is both scientifically grounded and utterly mind-bending. You will discover how time can slow to a crawl, how empty space holds more energy than all the stars combined, and how our entire cosmic neighborhood might be just one bubble in an infinite, frothing multiverse. These are not just abstract ideas for physicists in labs. They are the hidden forces shaping the reality you experience every single day, and understanding them changes how you see your place in the grand scheme of everything. So get ready to have your mind expanded in ways you never thought possible. We're about to challenge fundamental assumptions, uncover secrets hidden in plain sight, and explore concepts that are as beautiful as they are bizarre. This is more than just a list of facts. It's an invitation to look at the cosmos with fresh eyes, to feel that childlike sense of wonder and awe all over again. Buckle up, because we are about to embark on a cosmic ride through a universe far stranger and more incredible than you ever believed. And by the end, you will never see the night sky in quite the same way again. And that journey begins with a truth so fundamental it reshapes our entire cosmic address. We naturally tend to imagine the universe like a city, with a downtown core and suburbs stretching out to the edges. We might even instinctively feel that our own Milky Way galaxy is somewhere special, perhaps even near the center of everything. But the first and perhaps most humbling, surprising truth is this: the universe has no center. There is no grand central point, no cosmic capital from which everything expands. Every single point in the cosmos, from our own galaxy to the most distant one we can observe, has the same equal claim to being at the heart of the expansion. To understand this, we need to look at one of the most profound discoveries in human history. The universe is not just expanding, but space itself is stretching. The classic analogy is a loaf of raisin-bread dough as it bakes. Picture the dough as the fabric of space and the raisins as galaxies. As the dough rises, every single raisin moves away from every other raisin. From the perspective of any raisin you choose, all the others are receding. A raisin on the edge doesn't see itself as fleeing from a center. It sees all its raisin neighbors moving away. This is precisely what astronomers observe. No matter which direction we point our telescopes, distant galaxies are all moving away from us, and the further away they are, the faster they seem to be receding. This isn't because we are at the center of some grand explosion, but because the very space between all galaxies is continuously growing. This idea is grounded in what scientists call the cosmological principle, which simply states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the universe has a fairly uniform composition. One huge patch of space looks very much like any other huge patch. Isotropic means it looks the same in every direction you look. There are no giant walls of galaxies in one direction and empty voids in another when you zoom out far enough. This principle dismantles the ancient, deeply ingrained idea of a privileged location. For centuries, we thought Earth was the center of the solar system. Then we thought the Sun was the center of the galaxy. But this truth tells us there is no center. Our galaxy is just another raisin in an unimaginably vast, expanding loaf. This forces a profound re-evaluation of our place in the cosmos. We are not at the center of anything. We are, in a very real sense, in the middle of everything because every location is. It's a democratization of perspective on a cosmic scale, a reminder that the universe was not made for us, but that we are a beautiful and conscious part of its grand, centerless whole. If the idea of a centerless universe redefines our place in the cosmos, this next truth completely rewrites the inventory of what's actually out there. We gaze at the glittering tapestry of the night sky and feel we are seeing the universe in all its glory. But the shocking reality is that we are only perceiving a tiny, almost insignificant fraction of what exists. The stars, galaxies, nebulae, and every planet you've ever seen or heard of, all of that normal, tangible matter that we are made of accounts for less than 5% of the total content of the universe. Think about that for a moment. Over 95% of the cosmos is composed of substances that are completely invisible to us, entities we cannot see, touch, or directly measure, yet they dictate the ultimate fate of everything we can see. This is the domain of dark matter and dark energy, the two greatest and most perplexing ingredients in the cosmic recipe. Let's break down this cosmic pie chart, starting with dark matter. Imagine you're watching a merry-go-round spinning at a playground. From the way it moves, you can roughly estimate how heavy it is. Now, picture that same merry-go-round spinning at an incredibly high speed, so fast that, based on the weight of the children you see on it, it should instantly fly apart. Yet it holds together perfectly. Your only logical conclusion would be that there is some unseen, massive substance holding it all together, something you can't see but whose presence is undeniable through its gravitational effect. This is precisely how astronomers discovered dark matter. They observed galaxies and clusters of galaxies rotating so quickly that the visible stars and gas alone could not provide enough gravity to keep them from flinging themselves into the void. There had to be more mass, a huge amount of it, creating an immense gravitational scaffold that holds these cosmic structures together. We call this mysterious, invisible mass dark matter. It doesn't emit, absorb, or reflect any light, making it completely transparent, but its gravitational pull is the cosmic glue that binds galaxies and shapes the large-scale structure of the universe. But dark matter, as strange and dominant as it is, only makes up about 27% of the universe. The remaining 68%, the majority of everything that exists, is something even more bizarre and counterintuitive: dark energy. To understand its role, we need to return to the expanding loaf of raisin bread from our first truth. For most of the 20th century, scientists assumed that the gravitational pull of all the matter in the universe, both visible and dark, would be acting as a brake on this expansion. They expected that over time, the universe would either slow down its expansion gradually or perhaps even reverse and collapse in a big crunch. Then, in the late 1990s, two independent teams of astronomers made a discovery that turned cosmology on its head. By observing distant supernovae, they found that the expansion of the universe is not slowing down at all. It is accelerating. The galaxies are flying away from each other faster and faster as time goes on. Something is actively working against gravity, pushing space itself apart with ever-increasing vigor. This something is what we call dark energy. It appears to be a property of empty space itself, a repulsive force that grows stronger as the universe expands and more space comes into existence. So we are left with a cosmic budget that is profoundly humbling. The world we know and see, the realm of planets, stars, and life, constitutes a mere 5% of the total universe. 27% is the invisible, binding force of dark matter, and a whopping 68% is the mysterious, repulsive force of dark energy. This means we are essentially blind to over 95% of our own reality. We are like sailors on a vast ocean, able to see only the faintest froth on the waves, completely unaware of the immense, dark depths of water beneath us and the strange, powerful currents that are actually determining our course. The quest to identify the true nature of dark matter and dark energy remains one of the most pressing and exciting challenges in all of modern physics, a stark reminder that the universe is far more mysterious than it appears. Now, if most of the universe is invisible, what about the very stage upon which this cosmic drama plays out? We've been talking about space, but what is it really? For centuries, scientists thought of space as a static, empty backdrop, an unchanging void through which objects moved. But our third surprising truth shatters that notion entirely, revealing that space and time are not separate, passive entities. They are woven together into a single dynamic fabric, a four-dimensional continuum called space-time, and this fabric is not only real, it can bend, warp, and ripple. This is the heart of Albert Einstein's theory of general relativity, a concept that completely overhauled our understanding of gravity. To grasp this, let's retire the old idea of gravity as a mysterious, invisible force pulling objects together. Instead, think of the universe as a vast, taut, flexible rubber sheet. This sheet represents the four-dimensional fabric of space-time. Now, when you place a heavy object like a bowling ball in the center of this sheet, what happens? It creates a deep depression, a curve in the rubber. If you then roll a smaller object like a marble near this depression, the marble won't travel in a straight line. It will spiral inward, orbiting the bowling ball before potentially falling into the well. The marble isn't being pulled by a force in the traditional sense. It is simply following the curved path created by the heavy object's distortion of the sheet. This is the essence of Einstein's gravity. Mass and energy tell spacetime how to curve, and that curved spacetime in turn tells objects how to move. The Earth orbits the Sun not because the Sun is pulling on it with some invisible string, but because the Sun's immense mass has created a deep gravitational well in the spacetime around it, and Earth is simply rolling along the contour of that curved space, like a car following a banked curve on a racetrack. This isn't just a beautiful theoretical idea. We have direct, observable proof that this bending is real. One of the most stunning pieces of evidence is a phenomenon called gravitational lensing. Imagine a massive object like a galaxy cluster sitting between us and an even more distant galaxy. The immense mass of the foreground cluster acts like a cosmic lens, warping the spacetime around it so profoundly that it bends the very path of light coming from the distant galaxy. From our viewpoint, this can create multiple images of the same background galaxy, or stretch it into bright, luminous arcs and rings around the foreground cluster. It's as if the galaxy cluster is a magnifying glass embedded in the fabric of the universe, distorting our view of the light behind it. Astronomers use this effect regularly to study objects that would otherwise be too far away and faint to see, and its precise measurements always confirm Einstein's predictions. But perhaps the most dramatic confirmation came just a few years ago with the first direct detection of gravitational waves. If spacetime is a fabric, then gravitational waves are the ripples that race across that fabric when it is violently disturbed. Picture the surface of a still pond. If you toss a pebble into it, concentric ripples spread outwards. Now, imagine the most cataclysmic events in the cosmos, two black holes, each with masses tens of times that of our Sun, spiraling inward at nearly the speed of light and finally colliding in a fraction of a second. This cosmic collision is like tossing not a pebble, but a mountain into the pond of spacetime. The impact sends powerful ripples, gravitational waves, outward across the universe, stretching and squeezing spacetime itself as they pass. In 2015, the LIGO Observatory felt this subtle stretching and squeezing, a vibration thousands of times smaller than the nucleus of an atom. confirming a 100-year-old prediction of general relativity. We are now literally listening to the echoes of these space-time tremors, a completely new way of observing the universe that proves its fabric is not just a theoretical abstraction, but a physical, dynamic entity that can be probed and measured. The universe, it turns out, is not a rigid stage. It is a flexible, living membrane, and every massive object in it is leaving its own unique imprint on its shape. And if the very fabric of space is flexible, then what does that mean for time, the other half of the space-time continuum? This leads us to our fourth surprising truth, one that directly challenges our most fundamental daily experience. Time is not absolute. There is no single, universal clock ticking away at the same rate for everyone, everywhere. The flow of time itself is malleable. It can stretch and slow down depending on how fast you are moving and the strength of the gravity you are experiencing. This isn't science fiction. It's a direct, proven consequence of Einstein's special and general theories of relativity, and it completely shatters our intuitive sense of a steady, constant temporal rhythm. Let's start with motion. According to Einstein's special relativity, the faster you travel through space, the slower your clock ticks relative to someone who is stationary. This phenomenon is called time dilation. Imagine a pair of identical twins. One, an astronaut, boards a spaceship and embarks on a journey at a significant fraction of the speed of light, let's say 90%. The other twin remains safely on Earth. From the Earth-bound twin's perspective, watching through a powerful telescope, everything inside the speeding spaceship would appear to be moving in slow motion. The astronaut's heartbeats, the blinking of the ship's lights, the flipping of calendar pages, all of it would be measurably slower. When the astronaut finally returns home after what felt like, for them, a 5-year mission, they would step out of the ship to find their Earth-bound sibling has aged 10, 20, or even more years. The astronaut didn't just feel like time passed slowly. For their biological clock and every physical process on their ship, time literally dilated, it stretched out. This happens because space and time are inextricably linked. As you approach the cosmic speed limit of light, your velocity through space must be paid for with a reduction in your rate of time. All of your speed is borrowed from the future, slowing your personal present to a crawl. But speed isn't the only factor. Gravity, or the curvature of space-time we just discussed, is an equally powerful time-warping agent. This is the realm of general relativity. The stronger the gravitational field you are in, the more time slows down. Picture a black hole, an object with gravity so intense that not even light can escape. If you could hover safely just above its event horizon, your clock would tick unbearably slowly compared to a clock on Earth. To a distant observer, you would appear to be frozen in time, your movement stretched across eternity. We don't need a black hole to see this, however. The effect is measurable right here in our solar system. Every single one of the GPS satellites orbiting our planet contains an incredibly precise atomic clock. These satellites are both moving very fast relative to the Earth's surface and are in a slightly weaker gravitational field because they are farther from the planet's center. Special relativity says their high speed should make their onboard clocks run slower than clocks on the ground, while general relativity says their weaker gravity should make their clocks run faster. It turns out the gravitational effect is stronger, so the satellite clocks ultimately run faster by about 38 microseconds per day. That might sound negligible, but in the world of GPS, where timing is everything and light travels nearly a foot per nanosecond, an uncorrected error of 38 microseconds would cause the entire system to accumulate positioning errors of over 6 miles per day, rendering it useless. So, the engineers must pre-program the satellite clocks to tick slightly slower before launch, building in the relativistic correction. Your phone's navigation app is a daily, practical proof that Einstein was right. Time is truly relative. This truth forces us to abandon the comforting idea of a single, shared now. your now, and my now are only synchronized if we are at rest relative to each other and in the same gravitational field. The universe operates not with one master clock, but with a countless multitude of personal times, each one valid for the observer experiencing it. There is no privileged present moment. The flow of time is a deeply personal and local experience, woven into the very fabric of your motion and your place in the gravitational landscape of the cosmos. Yet for all its bending and warping, this fabric of space-time presents us with another, quieter illusion. We move through a world that feels solid and substantial. The ground beneath your feet feels firm. The screen you're looking at feels like a continuous, tangible object. But this fifth surprising truth pulls back the curtain on that daily experience to reveal a shocking cosmic secret. The universe and everything in it is almost entirely empty space. The solidity we perceive is a grand and persistent illusion, a trick of the senses and the forces that govern the microscopic world. To understand this, we need to take a journey inward, down to the very building blocks of matter itself. Let's start with a simple object like your own hand. It feels solid and whole. Now, let's imagine zooming in far beyond the capabilities of any ordinary microscope. We pass through the layers of skin, diving into a single cell. We go further, arriving at the molecular level, and finally, we reach the atomic realm. This is the foundation of all normal matter, and what do we find here? An atom is often pictured like a miniature solar system, with a dense nucleus at the center and tiny electrons whizzing around it in orbits. While this model is a simplification, it perfectly illustrates the core truth about emptiness. The nucleus of an atom, which contains over 99.9% of its mass, is incredibly small. If you could magnify a hydrogen atom to the size of a football stadium, the nucleus at the center would be about the size of a single pea on the 50-yard line. The electrons, those vanishingly small specks of negative charge, would be buzzing around somewhere in the outer seats, like a few grains of sand lost in the vastness of the entire arena. And what fills the staggering distance between that pea-sized nucleus and the distant electrons? Nothing. A perfect, complete vacuum. It is not filled with air or any other substance. It is pure, unadulterated empty space. This structure means that an atom is over 99.999999999% empty space. All the tangible matter you have ever touched, every person, every mountain, every star, is composed almost entirely of this void. This leads to a thought experiment that is as unsettling as it is illuminating. Consider the 7.8 billion people that make up the entire human population of Earth. Every single one of us is composed of atoms, each one a tiny speck of mass floating in a colossal sea of nothingness. Now imagine a cosmic magic trick. If you could somehow reach in and squeeze out all the empty space from within every single atom in every single person. If you could compress all those tiny nuclei and electrons until they were touching, what would be left? The entire human race, all 7.8 billion of us, would be condensed into a volume smaller than a standard sugar cube. That tiny, incredibly dense cube would contain all the actual solid stuff, the mass of every human being on the planet. The rest of the space we appear to occupy, it's an illusion of structure, a ghostly architecture held together by forces, not by substance. So why then does anything feel solid at all? Why doesn't your hand simply pass through your desk when you lean on it? The answer lies not in the solidity of matter, but in the powerful forces that govern the interactions between these mostly empty atoms. The electrons that orbit the nucleus are bound by the electromagnetic force. When you push your hand against a table, the electrons in the atoms of your skin are repelled by the electrons in the atoms of the table. This electromagnetic repulsion is what you experience as solidity. It's not that two solid objects are meeting. It's that two powerful, invisible force fields are pushing against each other with immense strength. You are not really touching the table in the sense of two solid surfaces making contact. You are feeling the repulsive force of its electron cloud pushing back against your own. The universe is essentially using powerful energy fields to create the illusion of solidity, allowing these vast, empty constructs to interact in a way that creates the stable, tangible world we navigate every day. This profound emptiness is the default state of the cosmos, and it forces us to recognize that what we perceive as reality is a carefully constructed interface, a user-friendly illusion that allows us to function, while beneath the surface, the true nature of existence is a breathtaking and mostly empty void. If you think the emptiness of matter is a staggering concept, prepare for a truth that challenges the very nature of reality and your own unique place within it. We just explored how the solid world is an illusion built on a foundation of mostly empty space. But what if that foundation itself is constantly splitting, creating new versions of the cosmos with every fleeting moment? This brings us to one of the most mind-expanding ideas in all of physics, the multiverse. Specifically, we're diving into the many worlds interpretation of quantum mechanics, a concept that suggests there might not just be one universe, but an infinite number, and in that limitless expanse, there could be an infinite number of versions of you. To understand how this could possibly be, we need to venture into the bizarre world of the quantum, the realm of atoms and subatomic particles. In this domain, particles don't behave like tiny billiard balls. They exist in a fuzzy state of potentialities called a superposition. This means a particle, like an electron, isn't definitively in one place or another until we measure it. It exists as a cloud of probabilities, a wave of could be here and could be there simultaneously. The traditional, or Copenhagen, interpretation of quantum mechanics says that this wave of possibilities collapses into a single, definite reality the moment it is observed. It's as if a spinning coin, which is both heads and tails while it spins, is forced to land on one outcome when you catch it. The many worlds interpretation proposed by physicist Hugh Everett in the 1950s offers a radically different explanation. It says the wave never collapses. Instead, at the moment a quantum event has multiple possible outcomes, the universe itself splits. Every single possibility is realized, but each one plays out in its own newly branched, fully real universe. In one universe, you measure the electron and find it here. In another, absolutely identical universe that just branched off, you measure the exact same experiment and find the electron there. There is no single outcome. There are all outcomes, each one existing in its own separate, non-communicating branch of reality. This isn't a one-time event. This branching is happening constantly at every quantum juncture for every particle everywhere at every moment. The number of parallel universes being spawned is beyond any human comprehension, an endless, bubbling foam of alternate realities. Now extend this idea from electrons to your own life. Every decision you've ever made, from the monumental to the mundane, involved a quantum process in your brain. Which job should I take? Should I ask this person out on a date? Do I turn left or right at this street? According to the many worlds view, at the moment of each choice, the universe split. In one branch, you took the job in your hometown. In another, you moved across the country for a different career. In one reality, you mustered the courage and had a wonderful life with the person you loved. In another, you hesitated and never saw them again. There is a universe where you turned left and had a perfectly ordinary day, and a universe where you turned right and encountered a chain of events that changed your life forever. Every possible version of your life that could exist, based on every possible combination of choices and random quantum events, does exist somewhere in the vast multiversal tree. The version of you reading this script right now is just one thread in an infinite tapestry of selves. The philosophical implications of this are staggering. It redefines concepts of regret, fate, and identity. That path not taken wasn't just lost to memory, it was taken by another you in a world just as real as this one. Your consciousness, the feeling of you, is simply experiencing one single path through this endlessly forking labyrinth. The mathematics behind quantum theory, the Schrödinger equation, actually supports this view beautifully. It describes a wave function that smoothly and continuously evolves without any mysterious collapse, and the many worlds interpretation takes that math at face value. While it remains a controversial idea because it posits countless universes we can never observe, it solves some of the deepest puzzles in quantum mechanics. So, as you go about your day, consider the quiet, incredible possibility that with every breath you take, the cosmos is fracturing into endless new worlds, each one hosting a different story, a different triumph, a different tragedy, for the countless other yous navigating their own unique realities. Just as we grapple with the idea of infinite parallel realities, we encounter a truth that strikes at the very bedrock of science itself. We take for granted that the universe operates according to fixed, immutable laws, that gravity today is the same as it was 10 billion years ago, and that the forces binding atoms together are constant across time and space. But what if this foundational assumption is wrong? Our seventh surprising truth proposes exactly that. The laws of physics, the fundamental constants that govern reality, might not be constant at all. They could be slowly changing, evolving over the immense span of cosmic time. To understand how radical this idea is, think of the universe's operating manual. This manual has certain key numbers known as fundamental constants that dictate the strength of nature's forces and the properties of matter. One of the most important is the fine structure constant, often denoted by the Greek letter alpha. This number controls the strength of the electromagnetic force, the force responsible for holding atoms together, for chemical reactions, and for the very light we see. If alpha were just a few percent different, the universe would be unrecognizable. Stars might not form, carbon atoms might not exist, and the complex chemistry necessary for life would be impossible. For decades, physicists have assumed this number is, as its name implies, constant throughout the universe and across all time. But then, astronomers began looking back in time. By observing the light from incredibly bright and distant objects called quasars, which are the active supermassive black holes at the centers of ancient galaxies, we can effectively perform cosmic archaeology. The light from these quasars has been traveling for billions of years to reach us. As it journeys through the cosmos, it passes through enormous clouds of interstellar gas. Atoms in these clouds absorb specific wavelengths of the quasar's light, leaving behind a unique fingerprint, a barcode of dark lines in the quasar's spectrum. The precise positions of these lines are determined by the value of the fine structure constant at the time and place the light was absorbed. When scientists meticulously analyzed this ancient barcode, they found something astonishing. The absorption lines were not exactly where our current local laws of physics predicted they should be. The data suggested that billions of years ago, in certain directions of the sky, the fine structure constant was slightly smaller than it is today. The electromagnetic force was a tiny bit weaker in the distant past. The change is minuscule, only a few parts in a million, but if confirmed, its implications are cataclysmic for our understanding of physics. It would mean that the cosmos is not governed by a single, eternal set of rules, but by a framework that is itself in flux. The potential reasons for this are as profound as the discovery itself. Some theories in particle physics, particularly those attempting to unify all the fundamental forces, actually predict that constants could vary. They might be tied to the expansion of the universe itself, slowly evolving as space stretches. Or, even more wildly, these constants might not be uniform across the entire cosmos. Perhaps in one region of the universe, the fine structure constant is one value, allowing for stars and galaxies, while in another, it's different, creating a barren and sterile void. Our local, observable universe might just be one hospitable pocket in a vastly larger and more varied cosmos where the very rules of the game are different. Consider what this means for the stability of reality. The universe seems finely tuned for life, but if the constants are drifting, this fine-tuning isn't a permanent feature. It could be a temporary, local coincidence. Life may only be possible during a specific cosmic era when the constants have drifted into a narrow, habitable window. The ground beneath our feet feels solid, and the stars above seem stable, but this could be an illusion of our brief human timescales. On a cosmic timeline spanning billions of years, the very fabric of reality might be slowly unraveling or reweaving itself into new patterns with consequences we can scarcely imagine. The quest to confirm these varying constants continues, pushing our telescopes and instruments to their limits, because the answer will determine whether our universe is a castle built on eternal stone or a sand sculpture on the shore of time, constantly being reshaped by a changing tide. While black holes have long been portrayed as the ultimate cosmic prisons from which nothing, not even light, can ever return, our eighth truth reveals a stunning loophole in this seemingly absolute law. They are not the eternally dark, unchanging voids of classical physics. Instead, they possess a faint glow, a subtle heat, and because of this, they have a finite lifetime. This revolutionary idea comes from the mind of Stephen Hawking, who brilliantly merged the large-scale gravity of Einstein with the fuzzy, probabilistic rules of the quantum world to arrive at a breathtaking conclusion: black holes can and do evaporate. To understand how something that consumes light can possibly emit radiation, we need to visit the very edge of a black hole, the event horizon. This is the point of no return, the invisible boundary beyond which the gravitational pull is too great for anything to escape. But according to quantum field theory, empty space is not truly empty. It is a seething, boiling sea of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence from the raw energy of the vacuum, borrowing energy from the universe for an incredibly brief moment before annihilating each other and paying the energy back. This constant, frantic activity is happening everywhere, all the time, and usually, it's completely undetectable as the particles vanish as quickly as they appear. Now, imagine this quantum froth occurring right at the precipice of a black hole's event horizon. One of these virtual particle pairs appears. In a fantastically rare but consequential event, the two particles don't get a chance to annihilate. The intense tidal gravity of the black hole can tear the pair apart just as they form. One particle falls across the event horizon, plunging into the black hole, while its partner manages to escape, flying off into space as a real particle. From the perspective of an outside observer, the black hole has just emitted a particle. This is Hawking radiation, but there's a cosmic price to be paid for this emission. The law of energy conservation must be upheld. The particle that escaped carried positive energy away from the black hole. To balance the books, the particle that fell in must have had negative energy relative to the outside universe. When this negative energy is added to the black hole, it effectively reduces the black hole's total mass. So, with every pair of virtual particles that is ripped apart at its edge, the black hole loses a tiny, tiny amount of mass. It is slowly, inexorably evaporating. This process means that black holes are not completely black, they have a temperature. Hawking calculated that this temperature is inversely proportional to the black hole's mass. A giant stellar mass black hole with the mass of several suns would have an incredibly low temperature, just a tiny fraction of a degree above absolute zero. Its Hawking radiation would be so feeble and weak that it would be completely drowned out by the cosmic microwave background radiation, the leftover heat from the Big Bang. For such a massive black hole, the rate of evaporation is negligible, and it would take an almost unimaginable length of time, far, far longer than the current age of the universe, to lose a significant amount of mass. But for a very small black hole, the story is different. A black hole with the mass of a small asteroid would be incredibly hot, glowing with intense Hawking radiation and evaporating in a spectacular final burst of energy. This leads to one of the most profound consequences of Hawking's work. Black holes have a lifespan. They are not permanent fixtures of the cosmos, given enough time, and we are talking about timescales so vast they defy human comprehension. Every black hole in the universe will eventually radiate away all of its mass and vanish. A stellar black hole might take 10 to the power of 67 years to evaporate, a number with 67 zeros after it, but the process is inevitable. This completely transforms our view of black holes from static, eternal tombs to dynamic, evolving objects with a birth, a long life, and a dramatic death. However, this beautiful theory creates a monumental problem, one of the greatest puzzles in theoretical physics, the black hole information paradox. In quantum mechanics, information is never truly lost. If you burn a book, in principle, a being with godlike knowledge could collect every single smoke particle, every ash, and trace every photon of light to reconstruct the exact original state of the book. The information about which atoms were where is scrambled, but it is not destroyed. Black holes, however, seem to break this fundamental rule. Imagine you throw a book into a black hole. The book is made of particles with specific properties: mass, charge, spin. That is information. According to Hawking's original calculation, the radiation leaking out from the black hole is entirely thermal. It's random heat, like the glow from a stove element, and it carries no information whatsoever about what fell in. It doesn't matter if you threw in a book, a piano, or a collection of feathers, the Hawking radiation would be identical. So when the black hole finally evaporates and vanishes, what happened to the information that made up the book? If it is truly lost forever, then a cornerstone of quantum physics is wrong. This paradox has driven physicists to the edge of their understanding for decades. Some propose that the information is somehow encoded in the Hawking radiation in an incredibly subtle and complex way that we don't yet understand. Others have suggested radical new ideas about the nature of spacetime itself, like the firewall hypothesis, which posits that a wall of ultra-high-energy particles might exist just inside the event horizon, destroying anything that crosses and potentially preserving information. The resolution to the information paradox is likely to require a theory of quantum gravity, a framework that successfully unites general relativity with quantum mechanics. So, Hawking's discovery not only gave black holes a temperature and a finite life, but also opened a direct window into the deepest secrets of reality, challenging us to reconcile our two most powerful descriptions of the universe and proving that even the darkest objects in the cosmos are capable of shining a brilliant light on the laws of physics. Just when we thought we had a handle on the cosmic expansion, a discovery at the end of the 20th century sent shockwaves through the world of cosmology, revealing that the universe's growth isn't just continuing, it's speeding up. This ninth surprising truth confronts us with a cosmos that is not only expanding but is doing so at an ever-increasing rate, a runaway process driven by the mysterious force we call dark energy. The story of this discovery is a modern scientific epic, one that began with astronomers trying to measure the universe's expansion speed, known as the Hubble constant, and ended up completely rewriting its ultimate fate. For most of the 20th century, the prevailing view was that the universe, while expanding from the initial Big Bang, was likely doing so at a slowing pace. Imagine tossing a ball straight up into the air. Gravity acts as a brake, pulling the ball back down and slowing its ascent. Scientists thought the collective gravity of all the matter in the universe, the galaxies, the gas, and the immense amount of dark matter, was acting in the same way, tirelessly working against the momentum of the Big Bang to slow the cosmic expansion. The great debate was whether there was enough matter to eventually halt the expansion and pull everything back together in a big crunch, or if the universe would just keep expanding forever, gradually slowing to a crawl. Then, in the late 1990s, two competing teams set out to settle this question by looking at a specific kind of stellar explosion, a Type Ia supernova. These are not just any exploding stars, they are standard candles. A Type Ia supernova occurs in a binary star system where a dense white dwarf star steals matter from its companion. Once it reaches a very specific critical mass, it undergoes a thermonuclear detonation that is so uniform and so incredibly bright that it can outshine an entire galaxy. Because the intrinsic brightness is always nearly identical, astronomers can use these supernovae as cosmic mile markers. By carefully measuring how bright the supernova appears from Earth, they can calculate its distance with remarkable precision. And by analyzing the redshift of its light, how much the light waves have been stretched by the expansion of the universe, they can determine how much the universe has expanded since the star exploded. What both teams expected to find was that the most distant supernova, the ones whose light had been traveling for billions of years, would show signs of a universe that was expanding more rapidly in the past, confirming that the expansion had been slowing down. Instead, they found the exact opposite. The distant, ancient supernovae were fainter than their redshifts indicated they should be. This meant they were farther away than anyone had predicted. The only possible explanation was that the universe was expanding more slowly in the past than it is today. The expansion wasn't slowing down, it was accelerating. It was as if that ball you tossed in the air, instead of slowing down and falling back, suddenly kicked on a rocket engine and shot away from you faster and faster. This monumental discovery, which earned the leaders of the teams the Nobel Prize in Physics in 2011, pointed to the existence of a pervasive, repulsive force that is counteracting gravity on the largest scales. This force is what we now call dark energy. This astonishing finding was later powerfully confirmed by incredibly precise maps of the cosmic microwave background, the ancient afterglow of the Big Bang. This faint radiation is a snapshot of the infant universe, and by studying its subtle fluctuations, scientists can measure the universe's geometry, composition, and expansion history with exquisite detail. The data from satellites like Planck have independently verified that dark energy makes up about 68% of the total energy density of the cosmos, making it the dominant component of the universe and the driver of its accelerating expansion. This convergence of evidence from completely different methods, the relatively recent supernova and the ancient primordial light, cements the reality of our accelerating universe. This relentless acceleration leads to a profoundly lonely and cold ultimate fate, known as the heat death or the big freeze. In this scenario, the expansion of space, fueled by dark energy, continues to accelerate indefinitely. Over trillions upon trillions of years, galaxies outside our own local group will be pushed away by the stretching space between us, their light redshifted into oblivion until they fade completely from view. The universe will become a much darker and emptier place. Eventually, even within galaxy clusters, stars will burn through their fuel, dying out one by one until no new stars are born. Black holes will slowly evaporate via Hawking radiation over unimaginable timescales, and all that will be left is a sparse sea of subatomic particles and radiation, spread so thin by the ever-expanding cosmos that the temperature will approach absolute zero. This is a far cry from the dramatic, fiery Big Crunch once imagined. It is a slow, quiet, and irreversible descent into darkness and cold, a future where the cosmos becomes a vast, isolated, and incredibly lonely expanse. After exploring the vast emptiness of atoms and the strange evaporation of black holes, we arrive at a truth that is perhaps the most personally connecting of all. It bridges the unimaginable scales of the cosmos with the very substance of our being. The 10th surprising truth is both profoundly scientific and deeply poetic. We are all made of stardust. Every single atom in your body that is heavier than hydrogen, the carbon in your muscles, the oxygen you are breathing, the iron coursing through your veins was forged in the heart of a star that lived and died long before our sun was even a glimmer in the cosmos. You are not just living in the universe is living in you, a permanent record of ancient cosmic events. To understand how this is possible, we need to look at the life cycle of stars, the universe's ultimate element factories. In the beginning, after the Big Bang, the universe was a much simpler place, composed almost entirely of the two lightest elements, hydrogen and helium. For the rich complexity of planets and life to emerge, heavier elements like carbon, nitrogen, and oxygen needed to be created. This process is called nucleosynthesis, and it happens under the extreme pressures and temperatures found inside stars. A star like our Sun spends most of its life fusing hydrogen into helium in its core, releasing the energy that makes it shine. But for more massive stars, the story is far more dramatic. Once they have exhausted their hydrogen fuel, their immense gravity causes the core to contract and heat up even further, allowing it to begin fusing helium into carbon. This process continues in a nested series of shells like a cosmic onion. The star fuses progressively heavier elements, carbon into neon, neon into oxygen, and so on, all the way up to iron. Each step in this chain releases energy and forges a new, heavier element, building the periodic table one fusion reaction at a time. However, the process stops at iron. Fusing iron atoms does not release energy, it consumes it. With its energy source cut off, the star's core can no longer support the crushing weight of its own outer layers. In a cataclysm that can outshine an entire galaxy, the star collapses and then rebounds in a titanic explosion known as a supernova. The violence of a supernova is so immense, the energy so incomprehensibly high, that it provides the conditions necessary to forge all the elements heavier than iron. The gold in your jewelry, the silver in electronics, the uranium in the Earth's crust. In that fleeting, brilliant flash, the star scatters its newly forged elemental bounty far and wide, seeding the surrounding interstellar clouds with a rich mixture of life-giving ingredients. These stellar ashes, this cosmic fertilizer, become the raw material for new generations of stars and planets. Our own solar system is a direct product of this cycle. About 4.5 billion years ago, a cloud of gas and dust, enriched by the remnants of countless such supernovae, began to collapse under its own gravity. At its center, the Sun ignited. In the swirling disk of material surrounding it, dust grains of iron, silicon, carbon, and ice began to clump together, eventually forming the planets. The Earth itself is an aggregate of this stardust, and when conditions on our planet became just right, these same atoms began to assemble into complex molecules, forming the first self-replicating structures that would, over billions of years, evolve into the incredible diversity of life we see today. This means the calcium in your bones was once part of the skeleton of a massive star. The nitrogen in your DNA was fused in a stellar core that no longer exists. The oxygen you just inhaled was hurled across space by a supernova explosion that occurred billions of years ago. You are literally walking, talking collections of recycled cosmic material. This isn't a metaphor, it is our established cosmic genealogy. We are the universe becoming conscious of itself, a way for the cosmos to look back upon its own history and marvel at the beautiful, intricate chain of events that connects the deaths of ancient stars to the life flourishing on a pale blue dot. This brings us to a truth that might be the most challenging of all to our everyday perception of reality, a concept that calls into question the very nature of time itself. We experience life as a relentless flow, a river carrying us from the fixed past through the fleeting present and into the uncertain future. But what if this flow is the ultimate illusion? What if the past, present, and future are not successive chapters but exist simultaneously, laid out together in a single, frozen structure? This is the startling proposal of the block universe theory, a direct and profound consequence of Einstein's special relativity that suggests all of time, every moment that ever was or will be, already exists. To understand how this could be possible, we need to let go of thinking of time as a separate, flowing entity and instead see it for what relativity shows it to be, a dimension much like the three dimensions of space. Think about your own location. You can move forward or backward, left or right, up or down. In the block universe model, time is simply another one of these directions. We are all traveling through this four-dimensional space-time, but while we have some freedom to move through space, we are perpetually sliding in one direction through the time dimension at a fixed rate, a phenomenon we experience as the passage of time. Now imagine the entirety of this four-dimensional space-time as a vast, solid block. This block contains every single event that has ever happened or ever will happen, fixed in its location within the structure. Your birth is not a memory that has faded away, it is a specific coordinate in the block. Your life is not being written as you go, it is a long, twisting thread weaving through the block. And even your last moment on Earth is not an uncertain future event. It is another fixed point already present in the grand cosmic architecture. In this view, the universe does not happen. It simply is in its complete and total four-dimensional glory. This isn't just philosophical speculation. It arises directly from a key insight of special relativity called the relativity of simultaneity. Einstein showed that whether two events occur at the same time, whether they are simultaneous, depends entirely on your state of motion. There is no universal. Now, let's create a simple scenario. Imagine a person standing on a train platform, exactly halfway between two trees. At the precise moment they are in the middle, two bolts of lightning strike the two trees simultaneously. From their perspective, the light from both strikes reaches their eyes at the same instant, so they correctly conclude the strikes were simultaneous. Now picture someone looking out the window of a train speeding past the platform at near the speed of light. From their moving perspective, they are rushing toward the light coming from the tree ahead of them and away from the light coming from the tree behind. Consequently, they will see the forward lightning strike first and the rear strike later. For this observer, the two strikes were not simultaneous. Crucially, both observers are correct within their own reference frames. There is no privileged God's eye view that can declare one true present moment for the entire universe. If simultaneity is relative, then the very idea of a single objective now sweeping across the cosmos falls apart. Instead, every possible now for every possible observer exists with equal validity, all stitched together into the permanent fabric of the four-dimensional block. A powerful way to visualize this is to think about the world lines of objects. In the block universe, an object is not a point that moves through time. Instead, it is a long, string-like entity called a world line that stretches through the four-dimensional block from its beginning to its end. Think of a caterpillar. If you take a time-lapse photograph of it crawling across a log, you don't see a single caterpillar. You see a long, smeared trail representing its entire journey. In the block universe, that smeared trail is the caterpillar. Its entire life, from egg to adult, is a single, unchanging filament woven into the cosmos. You are not a static snapshot. You are your entire timeline, from your first breath to your last, all equally real and present. This completely reframes our understanding of existence. We feel we are at the moving tip of this world line, a point of consciousness we call the present, but according to the block view, the rest of the line is just as real. The child you once were still exists in the block, just as the elderly person you may become already exists. They are simply at different time coordinates, much like New York and Paris are at different space coordinates. This perspective forces us to confront deep questions about free will and destiny. If the future is already written into the block, do we truly have any choice? Philosophers and physicists grapple with this, and one compelling way to think about it is that our conscious experience of making decisions is an intrinsic part of the block structure. The block doesn't dictate your choices from the outside. It contains your process of deliberation, your weighing of options, and your final decision. Your journey of figuring things out is part of the immutable landscape. You are not a puppet on a string. You are the entire complex path of the puppet with all its twists and turns. The block universe doesn't necessarily rob us of free will. It may simply be the complete picture of all the free choices that are ever made. It's a perspective that can be either terrifying or liberating, suggesting that our lives are not fleeting moments destined to be lost to the past, but permanent and indelible features of the cosmic tapestry, with every cherished memory and every future hope forever fixed in the grand, static block of reality. Just when we thought the block universe presented a static picture of all time, another theory emerges that turns the very direction of time into a cosmic accident of perspective. We've grown accustomed to time's arrow flying in one direction, from the past through the present and into the future. But what if our forward-moving experience of time is simply a property of our particular corner of existence? What if, on the other side of the Big Bang, there exists a mirror universe where time flows in the opposite direction? This isn't just a whimsical thought experiment. It's a mathematically robust possibility known as the CPT symmetric universe, a concept that proposes our universe has a perfect twin where everything is reversed. To grasp this, we need to understand the three fundamental symmetries in physics, represented by the letters C, P, and T. C stands for charge conjugation, which means swapping every particle with its corresponding antiparticle. Imagine a world where electrons are replaced by positrons and protons by antiprotons. That's a charge-reversed universe. P stands for parity, which is like looking at the universe in a mirror. In a parity-reversed world, left becomes right, and the handedness of every particle spin is flipped. Finally, T stands for time reversal, which is exactly what it sounds like, running the clock backwards so effects precede their causes. For a long time, physicists believed that the laws of physics were perfectly symmetric under each of these three operations individually. But experiments in the mid-20th century revealed something shocking. These symmetries can be violated. For instance, certain radioactive decays show a preference for a specific handedness, meaning the universe at a fundamental level can tell left from right. Parity is not always conserved. However, here's the profound part. Physicists discovered that if you apply all three operations together, if you simultaneously reverse charge, parity, and time, the fundamental laws of physics appear to be perfectly symmetric. This is the CPT theorem, a cornerstone of quantum field theory. It suggests that if you could take our entire universe and create a perfect mirror image where every particle is replaced by its antiparticle, everything is spatially mirrored, and the flow of time is reversed, the resulting universe would obey exactly the same physical laws as our own. It would be a valid, self-consistent reality. In this CPT-transformed cosmos, what we call antimatter would be the normal matter. A left-handed neutrino in our world would be a right-handed antineutrino in that one. And most mind-bending of all, time would flow from what we consider the future toward what we call the past. This leads to a breathtaking cosmological speculation. What if the Big Bang didn't just create our universe, but in that moment of supreme symmetry, it also created its perfect CPT mirror, a twin universe evolving in the opposite temporal direction? From our perspective, time in that other universe is running backwards, but from the perspective of an observer in that mirror universe, their time feels normal and forward-moving, and it is our universe that appears to be evolving in reverse. In their reality, stars would form from scattered dust clouds collapsing inwards. Light would be emitted from their eyes and travel to objects, and they would remember the future while anticipating the past. This isn't about someone consciously deciding to move backwards. It's about the inherent direction of thermodynamic and causal processes being flipped. For them, the thermodynamic arrow of time, the progression from order to disorder, would point the other way. They would see shattered glasses assembling themselves on tables and feel knowledge fading into ignorance as they move through their personal past. This idea of a twin universe isn't merely a mathematical curiosity. It offers a potential solution to one of cosmology's great puzzles, the matter-antimatter asymmetry. Our observable universe is overwhelmingly composed of matter, with very little primordial antimatter. We don't fully understand why this is the case, as most theories suggest the Big Bang should have created equal amounts of both. The CPT symmetric universe model provides an elegant answer. It proposes that the Big Bang did in fact create a perfectly balanced cosmos, our matter-dominated universe moving forward in time, and an antimatter-dominated universe moving backward in time. The overall symmetry of the entire system is preserved, solving the mystery of the missing antimatter by positing that it all resides in the other, temporally reversed twin. Visualizing this is a powerful way to grasp the concept. Picture a split screen. On the left, we see our universe. A galaxy forms, a star shines, a civilization rises. On the right, we see the mirror universe, but we are viewing it from our temporal perspective. There, the sequence runs in reverse. The civilization fades away. The star gathers its light back into itself, and the galaxy unravels into a primal cloud of gas. Yet, for a conscious being within that right-hand universe, their experience would be just as real and continuous as ours. They would perceive their civilization's history as one of growth and discovery, not decline. The direction of time, it seems, might be the ultimate relative experience, a local condition rather than a universal decree. This speculative vision challenges our deepest intuitions about cause and effect, suggesting that the flow of time we hold so dear might not be a fundamental feature of the cosmos, but merely the view from our particular branch of a much larger and far more symmetrical reality. If you think the backward-flowing time of a mirror universe is strange, wait until you encounter a reality where the very act of looking at something forces it to make up its mind. We've explored how time and space are flexible, but now we venture into the quantum realm, where the rules of existence itself become fuzzy and probabilistic. The 13th surprising truth is a cornerstone of this quantum weirdness. Particles can be in two places at once. This isn't just a theoretical curiosity. It's a fundamental property of the universe at its smallest scales, a phenomenon known as quantum superposition. To understand superposition, let's leave behind our everyday experience with objects like baseballs and cars. In our macroscopic world, a ball is either in your hand or it's flying through the air. It has a definite location and state. But when we shrink down to the level of electrons, photons, and other quantum particles, this common-sense logic completely breaks down. A single electron is not like a tiny, hard ball. Instead, it exists as a cloud of probabilities. Before it is measured or observed, the electron does not have a single, defined position. It exists in a smeared-out state, being partly here, partly there, and partly everywhere else all at the same time. It is in a superposition of all its possible locations. The act of measuring it, shining a light on it, for instance, forces this probability cloud to collapse into a single, definite point. It's as if you had a magical coin that, while spinning, was genuinely both heads and tails, and only decided which side was facing up the very instant you reached out to catch it. This isn't a limitation of our measuring tools. It is how the universe actually operates at a fundamental level. The particle literally has no definite properties until an interaction pins it down. The profound and puzzling implications of this were brilliantly captured by physicist Erwin Schrödinger in his famous and famously morbid thought experiment, Schrödinger's cat. Imagine a steel chamber containing a cat, a radioactive atom, a Geiger counter, a hammer, and a vial of poison gas. The radioactive atom has a 50-50 chance of decaying within 1 hour. If it does decay, the Geiger counter will detect it, trigger the hammer to break the vial, and release the poison, killing the cat. If it does not decay, the cat remains alive. According to the rules of quantum mechanics, the radioactive atom exists in a superposition. It is both decayed and not decayed until it is observed. But since the fate of the cat is tied directly to the state of the atom, the entire system inside the box becomes entangled in this superposition. This means that until someone opens the box and looks inside, the cat itself must be considered both alive and dead simultaneously. It exists in a blur of two mutually exclusive realities, a living, purring creature and a deceased one, coexisting in a ghostly state of potential. Schrödinger devised this thought experiment not to suggest that cats can be undead, but to highlight what he saw as the absurdity of applying quantum weirdness directly to the everyday world. The paradox forces us to ask a critical question: where is the line? At what point does the fuzzy quantum world resolve into the definite classical world we experience? Does it require a conscious human observer to open the box and look, thereby collapsing the wave function and deciding the cat's fate? Or does the cat's own consciousness count? Or perhaps the interaction with the Geiger counter is enough. This is the core of the measurement problem in quantum mechanics, and it remains one of the most heated debates in physics. The act of observation seems to play a special, almost magical role in creating reality, suggesting that the universe may not be a collection of definite objects, but a tapestry of possibilities waiting to be actualized by interaction. It challenges the very idea of an objective reality that exists independently of us. This bizarre behavior isn't just philosophical, it has been confirmed by countless experiments. The double-slit experiment is the classic demonstration. When you fire a stream of electrons at a barrier with two narrow slits, they don't just form two lines on a detector screen behind it, as you might expect from little particles. Instead, they create an interference pattern of light and dark bands, a signature of wave behavior. This suggests each electron is acting like a wave and passing through both slits at the same time, interfering with itself. Even more astonishingly, if you fire the electrons one at a time, they still build up an interference pattern over time. Each individual electron must be going through both slits simultaneously and interfering with its own potential path. However, if you place a detector at the slits to determine which path a specific electron takes, the interference pattern vanishes. The mere act of measuring which slit the electron went through forces it to behave like a particle, collapsing its wave-like superposition and traveling through only one slit. The electron seems to know it is being watched, changing its behavior accordingly. This has been demonstrated not just with electrons, but with larger and larger objects, including entire molecules, pushing the boundary of where quantum behavior gives way to classical certainty. So, what does this mean for our understanding of reality? It suggests that the solid, definite world we perceive is, in a sense, an emergent property. At the deepest level, the universe is governed by probability and potentiality. Objects do not have inherent properties like location or momentum. They have a range of probable properties that only become fixed through interactions with their environment. This challenges the classical notion of locality, the idea that objects are only influenced by their immediate surroundings. In the quantum world, a particle's existence is non-local. It is spread out, and its properties are instantly correlated with other entangled particles, no matter the distance. The universe, it seems, is not a collection of separate, well-defined things, but an interconnected web of possibilities, and our act of observation is what weaves specific threads of this web into the tangible reality we call our own. It's a humbling and empowering thought. By simply looking at the world, we are not passive spectators, but active participants in the ongoing creation of the cosmos. But if particles can be in multiple states at once, what about the entire cosmos? Does the universe itself have a fundamental state, a baseline condition that permeates every corner of existence? It turns out it does. our 14th surprising truth reveals that the entire universe is not cold and dark in the way we might imagine. Instead, it is gently warmed by a faint, pervasive glow, a cosmic fossil from the very dawn of time. This is the cosmic microwave background radiation, and it means that even the deepest, most empty void of space has a measurable temperature of about 2.7 Kelvin, which is a frigid negative 455 degrees Fahrenheit. To understand the profound significance of this, we need to rewind the cosmic clock back to the very beginning. In the first moments after the Big Bang, the universe was an unimaginably hot, dense, and opaque soup of fundamental particles and energy. Light couldn't travel freely. It was constantly bouncing off and being absorbed by this seething plasma, much like being in the middle of an intensely dense fog. The universe was a brilliant, blinding fireball. Then, about 380,000 years after the Big Bang, a monumental transition occurred. The universe had expanded and cooled just enough for the first stable atoms to form, primarily hydrogen and helium. This sudden formation of neutral atoms was like the fog instantly clearing. For the first time, photons, particles of light, could travel unimpeded across the cosmos. This first flash of liberated light is what we now detect as the cosmic microwave background. It is the oldest light in the universe, a direct snapshot of the infant cosmos, and it has been traveling for over 13 billion years to reach our telescopes. The discovery of this background radiation in the mid-1960s was one of the greatest accidental breakthroughs in scientific history. Two radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were troubleshooting a persistent, annoying hiss in their large radio antenna. This noise was constant day and night and came from every direction in the sky. They scrubbed the antenna clean of pigeon droppings and checked every conceivable electronic fault, but the hiss remained. Unbeknownst to them, a team of physicists at Princeton had just calculated that if the Big Bang theory were correct, the entire universe should be filled with a faint, cool remnant radiation. When the two groups connected, the puzzle was solved. That persistent hiss wasn't an equipment malfunction. It was the echo of creation itself, the afterglow of the Big Bang. This discovery provided the smoking gun evidence that cemented the Big Bang as the dominant model of cosmic origins, earning Penzias and Wilson the Nobel Prize. What's truly remarkable is the uniformity of this background. When we map the entire sky, as satellites like COBE, WMAP, and the Planck mission have done with exquisite precision, we see that the temperature is incredibly even, varying by only about 1 part in 100,000. The universe is bathing us in a sea of microwave radiation that is almost perfectly smooth, but it's within those tiny 100,000th of a degree fluctuations that the real story lies. Imagine looking at a perfectly smooth sheet of paper only to discover under a powerful magnifying glass the most intricate and delicate texture. Those minuscule temperature variations, seen as faint blue and red splotches on the full sky map, are the seeds of all cosmic structure. They represent regions of the early universe that were ever so slightly denser or less dense than average. Over billions of years, gravity acted as an amplifier, pulling matter into those slightly overdense regions. The tiny ripples in the cosmic microwave background are the gravitational blueprints for everything we see today. The grand clusters of galaxies, the individual galaxies themselves, and the stars and planets within them, including our own Earth. Without those initial imperfections, the universe would have remained a featureless, expanding gas, and we would not be here to observe it. This universal background gives even the concept of empty space a new meaning. The vacuum between stars and galaxies is not a true nothingness. It is filled with this primordial light, a constant reminder of our hot, dense origin. If your eyes were sensitive to microwave radiation, the night sky would not be dark. Instead of blackness punctuated by points of starlight, you would see a uniform, dull glow in every direction you looked, a luminous curtain that is the faded remnant of the universe's fiery birth. The fact that we can measure this temperature so precisely and decode the story written in its faint wrinkles is a testament to human curiosity and our powerful tools for peering into the deepest past. The cosmic microwave background is our ultimate time machine, allowing us to stare directly at the afterimage of the Big Bang and read the initial conditions that set the stage for the entire cosmic evolution that followed. Just as we grapple with the universe's faint afterglow and the strange superposition of particles, we come to a truth that challenges the very definitions we use to describe reality. Light, the very messenger that allows us to see the cosmos, holds a secret identity. Our 15th surprising truth is the mind-bending concept of wave-particle duality, a cornerstone of quantum mechanics that reveals light, and indeed all quantum objects, are neither purely wave nor purely particle, but a perplexing combination of both, changing their behavior based solely on whether we are watching. To understand how bizarre this is, think about the classic ways we categorize things in our everyday world. A wave, like a ripple on a pond, is a spread-out disturbance. It can bend around corners, a property called diffraction, and it can interfere with itself where peaks and troughs add together or cancel out. A particle, like a tiny marble, is a localized point. It has a specific position and travels in a straight line, bouncing off walls one at a time. For centuries, scientists were locked in a fierce debate. Was light made of particles, as Newton argued, or was it a wave, as Huygens suggested? The evidence seemed to swing decisively in favor of waves when, in the early 19th century, Thomas Young performed his iconic double-slit experiment. He shone a beam of light at a barrier with two narrow, parallel slits. If light were made of simple particles, you would expect to see two bright lines on a screen behind the barrier, corresponding to the particles that passed straight through each slit. But that's not what happened. Instead, Young saw a series of light and dark bands known as an interference pattern. This is the unmistakable signature of wave behavior. It meant that the light waves passing through the two slits were spreading out and overlapping, with the peaks of waves from one slit meeting the troughs from the other, cancelling out to create dark bands and peaks meeting peaks to create bright bands. The case appeared closed. Light was a wave, but then the quantum revolution of the 20th century turned this settled science on its head. Albert Einstein, in his work on the photoelectric effect, showed that light could also behave as if it were made of discrete packets of energy, which we now call photons. When light hits certain metals, it kicks out electrons, but only if the light is above a specific color or frequency. This is a particle-like behavior. It's as if you were trying to knock down a wall with baseballs. Using 1,000,000 ping-pong balls, even with a lot of energy, won't do it, but one well-thrown baseball can. The energy comes in indivisible chunks, so which is it? Is light a wave or a particle? The utterly profound answer from quantum mechanics is, it is both, and its nature depends entirely on the question you ask, or more precisely, on how you choose to measure it. This brings us back to the double-slit experiment, but with a modern quantum twist. Imagine we can fire a beam of light so faint that we are sending individual photons toward the double slits, one at a time. You might expect each photon, as a particle, to go through one slit or the other and build up two bright lines on the detector screen, but that is not what occurs. Even when the photons are sent through one by one with plenty of time between them, an interference pattern still slowly emerges. This is astonishing. The only way a single photon can create an interference pattern is if it passes through both slits at the same time and interferes with itself. In the absence of an observer, each photon exists in a superposition of paths, behaving as a spread-out wave that explores all possible routes. Now for the truly reality-altering part of the experiment. Introduce a detector at the slits to determine which specific slit each photon travels through. The moment you do this, the interference pattern vanishes. Instantly, the screen shows only two bright lines. The act of measuring, of pinning down the photon's path, forces it to collapse from a wave-like superposition into a definite particle-like state, traveling through one slit or the other. It seems the photon knows it is being watched and changes its behavior to comply. This effect has been demonstrated not just with photons, but with electrons, atoms, and even large molecules, proving that this wave-particle duality is a fundamental property of the entire quantum world. The line between a spread-out wave and a localized particle is not a fixed boundary in nature, but is drawn by the very act of observation itself. This duality forces us to abandon our classical, intuitive pictures of the world. A quantum object does not have a definite path or location until it is measured. It exists as a cloud of probability, a wave of potentiality described by a mathematical entity called the wave function. This wave function evolves smoothly, exploring all possibilities, and it's only when a measurement occurs that this wave function collapses and a single, definite property is realized. The universe, at its most fundamental level, is not made of tiny billiard balls, but of entities that exist in a ghostly state of both and until forced into an either-or by interaction. Light is the perfect embodiment of this quantum enigma, a wave when traveling through space, allowing it to carry energy across the vast emptiness between stars, and a particle when arriving at a destination, delivering that energy in a localized packet to your eye or a solar cell. This dual nature is not a paradox to be solved, but a deep feature of our reality, reminding us that the cosmos is far stranger and more wonderfully complex than our everyday language can adequately describe. But if we've learned that the fabric of space-time is dynamic and that particles exist in ghostly superpositions, then what exactly is the stage upon which all this quantum drama plays out? We've been conditioned to think of the vacuum of space as the ultimate void, a perfect and absolute nothingness. Yet our 16th surprising truth reveals that this could not be further from reality. According to quantum field theory, what we perceive as empty space is not empty at all. It is a seething, bubbling, and frenetically active medium, a quantum foam teeming with transient particles and simmering with an immense underlying energy. The universe, even in its deepest and most remote voids, is never truly quiet or empty. To grasp this, we need to shift our perspective from thinking about particles as tiny, solitary balls to seeing them as mere excitations or ripples in invisible, omnipresent fields that fill all of space-time. Imagine the universe is an unimaginably vast, calm ocean. This ocean represents a quantum field. Now, a wave on that ocean is like a particle, a localized excitation in the field. An electron is a ripple in the electron field. A photon is a vibration in the electromagnetic field. But what happens when the ocean is perfectly calm? Is it completely still? Quantum mechanics says no. Even at its absolute calmest, the ocean still has a faint, intrinsic jitter, a residual energy that can never be removed. This is the zero-point energy of the quantum vacuum, and it has profound consequences. Because of this fundamental energy, the vacuum is not dormant. Particle-antiparticle pairs, known as virtual particles, spontaneously blink into existence everywhere all the time. They borrow energy from the universe for an infinitesimally short moment, as allowed by the Heisenberg uncertainty principle, before annihilating each other and returning the energy, vanishing back into the background field from which they came. This constant, frantic creation and destruction is often visualized as a bubbling foam, a quantum foam where spacetime itself is churned into a probabilistic froth at the very smallest scales, far smaller than a single atom. This isn't just a mathematical curiosity. We can observe the real, physical effects of this seething vacuum. One of the most elegant demonstrations is the Casimir effect, named after the Dutch physicist who predicted it. Imagine you take two perfectly smooth, uncharged metallic plates and place them incredibly close together in a perfect vacuum, parallel to each other with a tiny gap between them, smaller than the width of a human hair. In the vast, open vacuum outside the plates, virtual particles of all possible wavelengths can pop in and out of existence. But in the narrow gap between the plates, only virtual particles with specific wavelengths that can fit between the plates are allowed to appear. This creates an imbalance in the quantum pressure. There are simply more virtual particles forming outside the plates than between them. The result, the greater external pressure, literally pushes the two plates together. It's a minuscule force, but it is measurable, and experiments have confirmed it exactly. This is not some mysterious force or chemical attraction. It is the direct physical push of the vacuum energy itself, proving that empty space exerts a tangible pressure. The implications of this are staggering. First, it means that the very concept of nothing may be a human illusion. There is no such thing as a true void in the universe. Every cubic centimeter of space, no matter how remote, is filled with this roiling quantum activity. Second, this zero-point energy of the vacuum might be the most dominant energy source in the entire cosmos. Calculations suggest its energy density is astronomically high, so high that it creates one of the greatest unsolved problems in theoretical physics, the cosmological constant problem. Our theories predict a vacuum energy so colossal that it should cause the universe to expand at a rate that would tear galaxies, planets, and even atoms apart almost instantly. Yet, when we measure the actual expansion driven by dark energy, it is many, many orders of magnitude weaker. Why is the observed effect of the vacuum energy so much smaller than our calculations suggest? This discrepancy remains a deep mystery, hinting that there is something fundamental about gravity or quantum theory that we still do not understand. So, the next time you look up at the serene, dark expanse of the night sky, remember that you are not gazing into an empty void. You are looking at a cosmos that is fundamentally, unceasingly alive. Beneath the apparent stillness lies a hidden ocean of furious activity, a quantum simmer that is the true baseline state of reality. This vibrant vacuum is not just a passive container for the universe. It is an active participant, its fleeting virtual particles and immense latent energy shaping the behavior of everything from the smallest subatomic particles to the grandest cosmic structures. The silence of space is a grand and profound illusion, masking a reality that is perpetually and beautifully in flux. Moving from the vibrant, energetic vacuum to the particles that dance within it, we encounter what might be the most radical and mind-bending hypothesis ever proposed about the nature of reality. What if every single electron you have ever encountered, the ones flowing through the wires in your walls, the ones orbiting atoms in your body, and the ones flying through the most distant galaxies, was not a distinct entity, but just a single, solitary electron? This is the outrageous, beautiful, and almost certainly incorrect idea put forward by the legendary physicist John Archibald Wheeler in a phone call to his student Richard Feynman. It's a concept so strange it seems ripped from the pages of science fiction, proposing that the entire cosmos, with its countless trillions upon trillions of electrons, is actually the elaborate time-traveling journey of just one. To understand how this could even be conceivable, we need to revisit a key insight from earlier, that positrons, the antimatter counterparts of electrons, can be mathematically described as electrons moving backwards in time. When a physicist draws a diagram of a particle interaction, a positron is represented as an electron's world line with an arrow pointing backwards along the time axis. Wheeler took this mathematical curiosity and asked a breathtakingly ambitious question. What if this isn't just a convenient drawing trick? What if it's literally true? In his vision, there is only one electron in existence. This lone particle is not confined to moving forward in time like we are. Instead, it zigzags wildly throughout the entire history of the cosmos, darting forward into the future, then reversing course and traveling backward into the past, then forward again in an impossibly complex, knotted path that fills the entire spacetime continuum. Every time this single electron moves forward in time, we observe it as a normal, negatively charged electron. But every time it makes a U-turn and heads backward in time, we perceive that event as the creation of a positron. In this spectacularly economical model, the countless electrons and positrons we see are merely different moments in the life story of this one primordial traveler. This idea offers a uniquely elegant solution to two profound mysteries in physics. The first is the perfect uniformity of all electrons. Every electron in the universe has exactly the same mass, the same charge, and the same spin. They are utterly identical, perfect clones of one another. If they were all truly separate particles, this perfect symmetry would be a remarkable and unexplained coincidence. But if they are all just the same single particle appearing at different points in its timeline, their perfect sameness is automatic. You are just seeing the same thing over and over again. The second mystery it addresses is the existence of antimatter. In this model, antimatter isn't a separate substance. It's just ordinary matter seen from a reversed temporal perspective. The creation of an electron-positron pair out of energy is simply the moment our lone electron decides to turn around and head back in time, creating two observable particles from its one world line. Similarly, when an electron and a positron meet and annihilate, that's just the point where the electron finishes its backward journey and turns around to head forward once more. Imagine the visual of this. Picture the entire four-dimensional block universe, not as a static loaf of raisin bread, but as a single, shimmering thread of gold, the world line of the one electron. This thread doesn't run in a straight line. It weaves an impossibly intricate tapestry, darting forward from the Big Bang, turning around to create a positron in a distant nebula, racing forward again to be part of a dinosaur, then zipping backward to help power a star in the early universe. Its path is a tangled knot that intersects with every location where an electron or positron has ever been observed. The sheer abundance of these particles in the cosmos is not a measure of quantity, but a testament to the unimaginable busyness of this one fundamental entity, forever stitching itself through the fabric of reality to create the illusion of a populated universe. While this hypothesis is a stunning piece of creative physics, it is almost certainly not how our universe works. The most significant problem is a simple matter of accounting. If the universe truly contained only one electron zipping back and forth, the total number of electrons and positrons should be perfectly balanced. For every electron journeying forward, there should be a corresponding positron, a backward journeying segment somewhere else. But our observable universe is overwhelmingly dominated by matter. We see vast numbers of electrons but very few positrons, which would be incredibly rare and short-lived. This fundamental imbalance of matter over antimatter is a major cosmological puzzle, and it directly contradicts the prediction of a perfectly symmetrical, single electron universe. Furthermore, the idea struggles to explain other particle families. Where are the single quark or the single neutrino that would have to be performing their own time-bending ballets? Yet the profound value of Wheeler's thought experiment lies not in its truth, but in its audacity. It forces us to confront the sheer weirdness of the tools we use to describe reality, like the treatment of antimatter as time-reversed matter, and to ask where the boundaries of those tools lie. It demonstrates that when we push our best theories to their absolute limits, the universe they describe can become far stranger than any fiction, a place where a single, timeless entity could, in principle, be responsible for the entire complex dance of charged particles that makes up our world. It stands as a permanent monument to the power of human imagination in theoretical physics, a reminder that sometimes the most beautiful and elegant ideas, even if they are ultimately wrong, can illuminate the path toward a deeper understanding by showing us just how wonderfully bizarre the cosmos might have been. Now, as we continue to probe the deepest layers of reality, we arrive at a truth that sounds like it was lifted from the most far-fetched science fiction, yet it is a serious and compelling theory debated by physicists today. This is the idea that the universe we inhabit, with its rich three-dimensional depth, might be nothing more than a magnificent illusion, a cosmic hologram. The holographic principle suggests that all the information that makes up our reality, from the farthest galaxy to the feeling of your feet on the ground, is not actually stored within the volume of space itself, but is instead encoded on a distant, two-dimensional surface that surrounds us like the film on a soap bubble. We are not living inside the volume, we are living on a projection emanating from the boundary. The origins of this astonishing idea come from an unexpected place, the study of black holes and their perplexing relationship with information. We previously discussed Hawking radiation and the black hole information paradox, the puzzle of what happens to the information about stuff that falls into a black hole. In the 1990s, physicist Gerard T. Hooft and later Leonard Susskind, building on work by Jacob Bekenstein, made a revolutionary connection. Bekenstein had discovered that the maximum amount of information or entropy that a region of space can contain is not proportional to its volume, as you might expect, but to the surface area of its boundary. This is a profoundly non-intuitive concept. Imagine a box. You would naturally think that a bigger box with more volume can hold more stuff and therefore more information. But Bekenstein's work, applied to black holes, showed that the maximum information a black hole can hold is limited by the area of its event horizon, the surface that shrouds it. It's as if all the data describing every star, planet, and atom that ever fell in is painted onto the surface of the black hole's horizon like a cosmic fresco. Susskind and T. Hooft took this a step further, proposing that this isn't just a weird property of black holes, but a fundamental principle of the universe. All the information contained within any region of space is entirely encoded on the boundary of that region. This is the core of the holographic principle. To visualize how this could possibly work, think about an ordinary hologram on a credit card or a banknote. That shiny, two-dimensional surface, when illuminated with light, creates a stunning three-dimensional image that you can look around. All the data needed to reconstruct that full 3D image is contained on the flat 2D surface. The holographic principle posits that our entire universe operates in an analogous way. The three-dimensional world we experience, with its height, width, and depth, might be a projection from a vast, two-dimensional shell that exists at the absolute edge of the observable universe. Every event, every particle, every force we feel in our 3D world is just a translation of information stored on this distant, lower-dimensional surface. In this view, reality is not fundamentally three-dimensional. The third dimension is an emergent property, a convenient and convincing illusion generated by the complex processing of data on a 2D screen. The implications of this are enough to make your head spin. First, it suggests that the universe has a finite information content, much like a computer with a maximum storage capacity. There is a limit to how much stuff can happen in any given area, a fundamental pixelation of reality. This could provide a natural path toward unifying gravity with quantum mechanics, as the holographic principle arises directly from the marriage of these two domains in black hole physics. Second, it completely redefines the nature of space-time. Space and time may not be the fundamental stage of the cosmos. They could themselves be emergent phenomena, generated by the intricate entanglement of quantum bits of information on the boundary. The smooth, continuous space we move through might be a kind of average, large-scale approximation of a vast network of interconnected data points. This idea finds a concrete mathematical realization in what is known as the AD/S/CFT correspondence, a specific and powerful duality from string theory that provides a full dictionary for translating a gravitational theory in a warped, higher-dimensional space into a quantum field theory without gravity living on its boundary. It's a working, calculable example of holography in action. If this principle is true, it means you, the device you're using, and the room you're in are all incredibly detailed and consistent hallucinations. The solidity you feel and the distances you measure are not the primary reality. They are the output of a cosmic computation happening on a surface so far away we can never hope to see it. It paints a picture of the universe not as a container of things, but as a network of relationships where the information describing what happens here is intrinsically linked to what is written on the edge of everything. While the holographic universe remains a theoretical framework, it is one of the most profound and promising ideas in modern physics, forcing us to consider that the ultimate nature of existence might be far more alien and informational than we ever dreamed. A grand projection on the most magnificent screen imaginable. We've journeyed through a cosmos of holograms, single electrons, and quantum foam, but now we must face a truth that challenges the very concept of beginnings and endings. One of the most profound and widely accepted discoveries in modern cosmology is that time itself, the very framework of cause and effect, likely had a definitive starting point. According to our best models, time as we understand it began with the singularity of the Big Bang approximately 13.8 billion years ago. This isn't just the start of matter and energy exploding into a pre-existing void. It was the beginning of space-time itself. Before that moment, the very words before and after lose all meaning because there was no time for events to occur in. The Big Bang marks the edge of the cosmic calendar, the 0 point of history. To wrap your mind around this, consider a powerful visual. Imagine the entire timeline of the universe from its origin to the present day laid out like a ruler. At the 0 mark, you have the Big Bang. To the right, the ruler extends for 13.8 billion years, marking the formation of the first atoms, the ignition of stars, the birth of galaxies, and the rise of life on Earth. But what about to the left of 0? What lies in the direction of before? According to general relativity, that part of the ruler simply doesn't exist. It's not that there's an empty, timeless void waiting there. The concept of there itself breaks down. The question, what happened before the Big Bang, might be as meaningless as asking, what is north of the North Pole? If you stand at the North Pole, every single direction you can point is south. There is no north of that point. In the same way, at the moment of the Big Bang, every possible direction in space-time points forward into the future. There is no before to point to. This isn't a failure of our imagination. It's a limitation embedded in the geometry of the cosmos as described by Einstein's equations, which break down at the instant of the singularity. This conclusion is forced upon us by the overwhelming evidence for the Big Bang, particularly the expansion of the universe and the existence of the cosmic microwave background radiation. When we trace the expansion backwards, like rewinding a cosmic film, all the matter and energy we see gets compressed into an ever smaller, ever denser, and ever hotter state. The equations of general relativity predict that this rewind leads inevitably to a singularity, a point of infinite density and temperature where the laws of physics as we know them cease to function. At this singularity, the fabric of spacetime is so crumpled that it no longer provides a coherent stage for events. It's the ultimate edge of reality. This doesn't necessarily mean the universe popped into existence from nothing in a philosophical sense. It means that our current understanding of physics hits a wall, a boundary beyond which our concepts of time, space, and causality are no longer applicable. This truth confronts us with the stark limits of both our physical models and our human intuition. We are hardwired to think in terms of cause and effect, of one event following another in an endless chain. The idea of an absolute beginning, a first cause with no prior cause, is deeply unsettling. We instinctively want to know what triggered it, what the initial conditions were. But if time began then, there was no prior to contain a trigger. This is where physics brushes up against philosophy, and it has led to fascinating speculative theories. Some cosmologists propose models like the cyclical universe or the multiverse, where our Big Bang was just one event in a much larger meta-temporal structure. In the cyclic model, the universe undergoes an endless sequence of Big Bangs and Big Crunches, with time restarting in each cycle. In the multiverse scenario, our universe is one bubble in a vast, eternally inflating cosmos, and time within our bubble began with our bang, even if the larger multiverse has no beginning. These ideas are compelling, but they remain in the realm of theoretical exploration. For now, the standard model of cosmology presents us with a definitive starting gun for the cosmic race, a moment when the clocks truly started ticking, forever redefining our place in a universe that not only has unimaginable scale but also a definite birthday. Look up at the sky on a clear day, and you'll see a brilliant golden yellow disk shining down, an image so deeply ingrained in our minds that it's painted in every child's drawing and celebrated in countless songs and poems. We refer to it as the yellow sun, a warm and comforting presence that feels fundamental to our existence. But here is a truth that directly contradicts this everyday experience: the sun is not yellow. In reality, the light emitted by the sun, when seen from outside our planet's protective blanket of air, is pure, stark white. This isn't a minor technicality. It's a dramatic correction to a universal misconception, and understanding why reveals just how much our perception of reality is shaped and distorted by the very world we live on. To grasp why the sun is white, we need to think about the nature of its light. The sun is a G-type main sequence star, and its surface temperature of around 5,500 degrees Celsius causes it to emit light across the entire visible spectrum. It produces a nearly perfect balance of all the colors red, orange, yellow, green, blue, indigo, and violet. When your eyes receive this complete mix of wavelengths in roughly equal measure, your brain interprets it as the color white. This is the same principle behind the white light from a high-quality LED bulb, which blends different colors to appear neutral. If you could stand on the International Space Station and look directly at the sun, shielding your eyes from its intense brightness, you would see a blindingly white orb against the blackness of space. This is the sun's true color, unaltered and pristine. So, how does this brilliant white star transform into the yellow ball we see from the ground? The entire magical transformation is performed by Earth's atmosphere through a process called Rayleigh scattering. Our sky is filled with countless tiny molecules of nitrogen and oxygen, and these molecules are much better at interacting with shorter wavelengths of light, the blues and violets, than with the longer wavelengths like reds and oranges. As sunlight enters the atmosphere, it collides with these molecules. The blue and violet light gets scattered in all directions, bouncing from one molecule to the next until it fills the entire dome of the sky above us. This scattered blue light is the very reason our sky appears blue during the day. It's essentially a diffuse glow of sunshine being thrown across the heavens. But this scattering comes at a cost for the direct beam of sunlight traveling straight to your eyes. With a significant portion of its blue light stripped away and scattered across the sky, the remaining light that reaches you directly from the solar disk is now deficient in blue. What's left is a combination that is heavier in the yellow, orange, and red parts of the spectrum. Our brains perceive this modified, blue-depleted light as a warm yellow or even a pale orange, especially when the sun is low on the horizon at sunrise or sunset. During those times, sunlight has to travel through a much thicker slice of atmosphere, which scatters away even more blue light and allows more reds and oranges to come through, creating those spectacular fiery skies. The yellow sun we are so familiar with is therefore an atmospheric illusion, a filtered version of reality created by the same beautiful physics that paints our sky blue. This truth extends far beyond a simple color correction. It serves as a powerful metaphor for how our perception is always conditioned by our environment. We never experience the universe in its raw, unfiltered state. Our senses are mediated through layers of influence. In this case, the atmosphere acts as a literal lens, tinting our view of our closest star. It's a humbling reminder that our perspective is local and subjective. Just as the atmosphere changes the sun's color, our preconceptions, biases, and biological limitations filter our understanding of everything from the cosmos to ourselves. When we recognize that our most basic assumptions can be so dramatically skewed, it invites a necessary humility and a curiosity to look beyond the apparent, to seek out the pristine, unfiltered data, whether we're gazing at the stars or grappling with complex ideas. Imagine for a moment a compelling side-by-side visual. On one side, the sun as seen from space, a perfect, searingly bright white sphere set against the profound black of the cosmos. On the other side, the sun as we know it from Earth, a familiar, gentle yellow disk in a bright blue sky. Placed together, these two images tell a complete story. One shows the objective reality, the star as it truly is. The other shows our lived experience, the reality we have evolved with and grown to love. Both are valid in their own context, but only one reveals the unvarnished truth. This simple comparison underscores a profound principle of science. The journey to understanding often requires us to step outside our natural frame of reference, to see the world not just as it appears from our singular viewpoint, but as it exists in the grand, impartial scheme of the universe. After grappling with the true color of our sun and the deceptive filters of our own perception, we arrive at a truth that offers perhaps the ultimate perspective on our place in the cosmos. The numbers involved in astronomy are so colossal they often become abstract, but this next concept gives them a visceral, tangible weight. It is a truth that connects the familiar ground beneath our feet to the most distant corners of space. There are more stars in the observable universe than there are grains of sand on every beach and in every desert on our entire planet. Let's begin with the sand, something we can all picture and even feel. Imagine standing on a vast, sun-drenched beach, the warm grains shifting under your feet. You scoop up a handful, that's thousands of grains right there. Now, picture every beach along every coastline on Earth, the sprawling shores of every continent, every hidden cove, every popular tourist destination. Then expand your imagination to include all the world's deserts. Envision the endless, rolling dunes of the Sahara, the Arabian Desert, the Gobi, and the great Australian outback. Every single grain of sand in all of those immense landscapes, from the surface down to a depth of several feet, represents an almost inconceivable number. Geologists and mathematicians have actually done the calculations, estimating that Earth holds somewhere in the neighborhood of 7.5 times 10 to the power of 18 grains of sand. That's a 7 followed by 18 zeros, a number so large it's often written as 5 quintillion. Now let's turn our gaze upward. A single galaxy, like our own Milky Way, is home to a staggering number of stars. Current estimates suggest our galaxy contains between 100 and 400 billion stars. Our Sun is just one unremarkable member of this vast celestial city. But the Milky Way is not alone. For a long time, we could only guess at the number of galaxies in the cosmos. Then, in the 1990s, the Hubble Space Telescope performed a critical experiment. Astronomers pointed it at what appeared to be an empty, dark patch of sky, a region no larger than a grain of sand held at arm's length, and let it collect light for days. The result was the Hubble Deep Field image, and it was anything but empty. That tiny, seemingly insignificant speck of sky was filled with thousands of galaxies, each one a colossal island of billions of stars. Extrapolating from that single image across the entire celestial sphere, astronomers now estimate there are at least 100 billion galaxies in the observable universe, and likely 200 billion or even more. Now for the cosmic multiplication, let's take a conservative estimate: 100 billion galaxies, each with an average of 100 billion stars. Multiplying these two numbers together gives us 10,000 billion stars, or 10 sextillion. That's a 1 followed by 22 zeros. Compare that to our estimate for the grains of sand on Earth, 7.5 quintillion, which is a 7 followed by 18 zeros. The number of stars is at least 1,000 times greater, and potentially many thousands of times greater than the number of sand grains. Every time you visit a beach, you are walking on a surface that represents less than 1,000th of the stellar population of the cosmos. If each grain of sand on Earth were a single galaxy, then you might begin to approach the scale we're talking about. This comparison does more than just deliver a staggering statistic. It serves as a profound tool for humility and awe. We live on a world where a single desert can seem infinite to a human walking across it. The Sahara feels impossibly vast, an ocean of sand that has swallowed empires. Yet, all the sand from all the Saharas and all the beaches of the world combined is utterly dwarfed by the stellar census of the heavens. It recalibrates our sense of scale in the most dramatic way possible. Our planet is one world orbiting one star, which is one member of a vast galaxy, which is itself just one of hundreds of billions of others. In this cosmic context, the stage upon which all of human history has played out is smaller than the smallest speck of dust in the grandest cathedral imaginable. This isn't meant to make us feel insignificant, but to fill us with a sense of profound wonder. The universe is not just big, it is operating on a level of abundance and grandeur that defies human comprehension, a constant, silent reminder that there is infinitely more to reality than what we can see from our tiny, sandy shore. We naturally assume the closer you get to a fire, the hotter you'll be, so it seems logical that Mercury, the planet closest to the Sun, would hold the title for the solar system's hottest world. But the cosmos loves to defy simple logic, and here's a truth that perfectly illustrates why Mercury is not the hottest planet. That dubious honor goes to Venus, our cloud-shrouded neighbor. However, Mercury claims a far more dramatic and punishing record. It experiences the most extreme temperature swings of any planet in our entire solar system, a wild ride between inferno and deep freeze that makes it a world of terrifying contrast. Let's break down why Mercury, despite its prime front-row seat to the Sun, loses the overall heat championship. The key to this cosmic puzzle isn't just proximity, it's what a planet wears, or in this case, what it doesn't wear. Mercury is a bare rock, a world almost completely devoid of a meaningful atmosphere. Imagine standing right next to a blazing bonfire. You feel intense heat on the side of your body facing the flames, but your back, turned to the cold night air, is freezing. This is Mercury's existence. During its long daytime, which lasts about 59 Earth days, the surface directly under the Sun bakes relentlessly. With no atmospheric blanket to deflect or distribute the solar radiation, temperatures on the sunlit side can skyrocket to a searing 800 degrees Fahrenheit, hot enough to melt lead. It's a literally hellish landscape where any notion of solidity is pushed to its absolute limit. But then the planet rotates, and that same spot turns away from the Sun, plunging into a night that also lasts nearly 2 Earth months. This is where the absence of an atmosphere becomes a different kind of curse. On Earth, our cozy blanket of gases acts like a heat reservoir, trapping warmth and slowly releasing it through the night, preventing temperatures from crashing. Mercury has no such luxury. The heat it absorbed during the day simply radiates straight back out into the blackness of space. There's nothing to hold it in. Consequently, the nighttime temperatures on Mercury don't just drop, they absolutely plummet, diving to a bone-shattering -290 degrees Fahrenheit. That's colder than the freezing point of oxygen. The same patch of ground that was hotter than a pizza oven at lunchtime is, a few weeks later, colder than the surface of Pluto at midnight. This incredible temperature range of over 1,100 degrees is the most extreme in our solar system, a testament to the fact that being close to the heat source means very little if you can't hold onto the warmth. Now let's turn to Venus, the true heavyweight champion of heat. Venus is farther from the Sun than Mercury, but it possesses an atmosphere that is the stuff of nightmares. It's incredibly thick, composed almost entirely of carbon dioxide, with clouds of sulfuric acid, creating a runaway greenhouse effect of catastrophic proportions. Picture a car parked in the sun with all the windows rolled up. Sunlight streams in as visible light, heating up the seats and dashboard. They then re-radiate that energy as infrared radiation or heat. But the closed windows trap that heat inside, causing the car's interior temperature to soar far above the outside air temperature. Venus is that car on a planetary scale. Its dense atmosphere acts like a permanent, suffocating lid, allowing solar energy in but refusing to let the resulting heat escape. This trapped energy builds up relentlessly, baking the surface to a constant 864 degrees Fahrenheit, which is hot enough to melt spacecraft in minutes and makes Mercury's maximum daytime temperature feel almost mild by comparison. Venus is uniformly, unbearably hot everywhere on its day side, its night side, at its equator, and at its poles. This stark comparison between the two planets delivers a powerful lesson in planetary science, one with profound implications for our own world. An atmosphere is not just the air we breathe, it is a planet's primary climate control system. Mercury shows us what happens without one. A world of violent extremes where life as we know it would be instantly vaporized by day and flash frozen by night. Venus, on the other hand, demonstrates the opposite horror. A climate control system stuck permanently on high, creating a global pressure cooker. Earth sits in the precious, narrow band between these two extremes. Our atmosphere is substantial enough to distribute heat from the equator toward the poles, moderate the temperature difference between day and night, and maintain a greenhouse effect that is strong enough to keep our planet habitable, but not so strong that it triggers a runaway catastrophe. The fate of a world is written not just in its distance from its star, but in the delicate composition of its sky. Understanding the ferocious temperature swings on Mercury and the oppressive, steady heat of Venus gives us a deep appreciation for the incredible, life-sustaining balance we enjoy here on Earth, a balance that is far more fragile and remarkable than we often realize. Just when you thought you'd encountered every cosmic paradox, from universes contained in a single electron to the strange nature of time, we arrive at a truth that turns the very definition of a calendar on its head. On our world, a year is a long journey around the sun, a cycle of seasons marked by 365 sunrises and sunsets. But on Venus, the cosmic clockwork operates in a way that is utterly alien to our experience. The 23rd surprising truth is this: a single day on Venus is longer than an entire year on Venus. It's a statement that seems to defy logic, yet it is a direct consequence of the planet's peculiar, almost lazy, spin and its relatively swift journey around our star. To unravel this celestial conundrum, we need to carefully define what we mean by a day and a year. A year on any planet is the time it takes to complete one full orbit around the Sun. For Venus, this orbital period is a brisk 225 Earth days. It zips around the Sun faster than Earth does. A day, however, is a bit more nuanced. We typically think of a day as the cycle from one sunrise to the next, but astronomers call this a solar day. There's another definition, the sidereal day, which is the time it takes for a planet to complete one full 360-degree rotation on its axis relative to the distant fixed stars. It is the sidereal day on Venus that is astonishingly long. The planet takes 243 Earth days to spin around just once. So, while its year is 225 Earth days long, its rotational day is 243 Earth days. This means that if you could stand on the scorching surface of Venus, you would experience a birthday before you experienced a single sunrise and sunset. Now the plot thickens considerably because Venus doesn't just spin slowly, it spins backwards. This is known as retrograde rotation. If you were to look down upon the solar system from above the Sun's north pole, you'd see most planets, including Earth, rotating counterclockwise on their axes and orbiting in the same direction. Venus is the glaring exception. It orbits the Sun counterclockwise like everyone else, but it rotates on its axis clockwise. Imagine a ball rolling counterclockwise around a central point, but the ball itself is slowly spinning clockwise. This backward spin has dramatic consequences for a hypothetical Venusian sky watcher. Because of this retrograde rotation, the Sun on Venus would rise in the west and set in the east. Furthermore, the combination of this slow, backward spin and the planet's rapid orbit creates a solar day on Venus, the time from one noon to the next, that is a whopping 117 Earth days long. So, you would have a little over half a Venusian solar day to wait between one sunrise and the next, but the planet itself completes fewer than 2 full rotations for every 3 trips it makes around the Sun. The question, of course, is how did Venus end up in this topsy-turvy state? While we don't have a definitive answer, the leading hypothesis points to a violent and chaotic early history. Planetary scientists suspect that in the turbulent youth of the solar system, a colossal impact with a protoplanetary body could have literally knocked Venus upside down. This impact would have been so immense that it effectively reversed the planet's spin, setting it on its current retrograde course. Alternatively, or perhaps in addition, strong gravitational tidal forces from the Sun, acting over billions of years on Venus's dense atmosphere and molten interior, could have gradually slowed its initial rotation to a crawl and even flipped its axis. The planet's thick, massive atmosphere may also play a key role, creating friction with the surface that acts as a constant brake, sapping its rotational energy. This bizarre rotational state makes Venus a unique laboratory for understanding planetary formation and the powerful forces that can sculpt a world over billions of years, leaving it as a perpetual monument to cosmic chaos. Just as we contemplate the bizarrely slow spin of Venus, we encounter a monumental feature in our solar system that embodies both permanence and profound change. For centuries, astronomers peering through their telescopes at the giant planet Jupiter have been captivated by a swirling, crimson eye staring back from its turbulent atmosphere. This is the Great Red Spot, an anticyclonic storm of such immense scale and fury that it has become an icon of our cosmic neighborhood. It's a tempest that has raged for at least 400 years, a seemingly eternal landmark in the Jovian sky. Yet the 24th surprising truth reveals that this ancient storm is not the unchanging titan we once believed it to be. The Great Red Spot is shrinking, transforming before our very eyes, and its ultimate fate remains one of the solar system's most compelling mysteries. To truly appreciate the scale of this phenomenon, we need to step back and understand its history and sheer size. The first confirmed observations of a persistent spot on Jupiter date back to the 1600s, with astronomers like Giovanni Cassini noting its presence. For generations, it was understood as a fixed feature, a storm so vast that at its peak in the late 19th century, it was estimated to be over 25,000 miles across, wide enough to easily swallow 3 Earths side by side. Imagine a hurricane on Earth. The most powerful ones might span a few hundred miles and last for a week or two before dissipating over cold water or land. The Great Red Spot is a storm in a completely different league. It has no land to disrupt it, churning instead in a planet-wide atmosphere of hydrogen and helium. Its winds scream at speeds exceeding 400 miles per hour, and its roots are thought to plunge dozens of miles deep into the planet's interior. It's a self-sustaining atmospheric engine, powered by the internal heat of Jupiter itself and the complex dynamics of the jet streams that cage it, causing it to rotate counterclockwise with a period of about 6 Earth days. The stunning shift in our understanding began with consistent monitoring over the past century, and it accelerated dramatically with the arrival of spacecraft. While Earth-based telescopes showed hints of a gradual decrease, The Voyager missions in 1979 provided our first close-up look, revealing the spot to be about 14,000 miles across. Since then, a combination of ground-based observatories and the Hubble Space Telescope has kept a vigilant watch, documenting an unmistakable and accelerating trend. The storm is not only shrinking in diameter, but it's also changing its shape, becoming more circular as it contracts. Recent measurements show it now spans just slightly over 10,000 miles across, roughly 1.3 times the diameter of Earth. While still an enormous vortex, this represents a dramatic reduction from its historical grandeur. Furthermore, the storm's iconic brick red color has been fading, often appearing more of a salmon or pale orange in modern images. This visual transformation adds to the evidence that the internal dynamics of the storm are undergoing a fundamental shift. So, why is this centuries-old Leviathan dwindling? The honest answer is that planetary scientists are still working to solve this puzzle. One leading theory points to the complex interaction between the Great Red Spot and smaller storms and eddies within Jupiter's chaotic atmosphere. Observations from Juno and other missions have shown numerous smaller anticyclones and jet stream features occasionally impacting the periphery of the spot. These interactions could be acting like a cosmic food processor, chipping away at the edges of the larger storm, stealing its energy and momentum, and causing it to lose integrity and shrink. Think of a massive, powerful whirlpool in a river. If you start tossing smaller, counter-rotating whirlpools into it, you would disrupt its smooth flow, breaking it apart from the outside in. Another possibility involves changes in the internal energy sources that fuel the storm. While the spot is stable, it is not isolated. It's part of a vast, complex weather system. Subtle shifts in Jupiter's internal heat flow or in the planetary scale wind patterns that surround and confine the storm could be slowly starving it, reducing its vigor and its ability to maintain its once colossal size. The most profound question looming over these observations is whether the Great Red Spot is marching toward its eventual disappearance. Will future generations look at Jupiter through a telescope and see a blank face where the great storm once swirled? Some models suggest that the shrinking could stabilize, and the storm might persist for many more centuries in a smaller, more compact form. Other simulations indicate that the current rate of contraction could lead to its dissolution within our lifetimes, or at least within the next few decades. The truth is, we don't know. Jupiter is a dynamic, living planet, and we have only been studying it with modern tools for a blink of an eye in its multi-billion-year history. The transformation of the Great Red Spot serves as a powerful, real-time lesson in planetary science. It demonstrates that even the largest and most stable-looking features in our solar system are not permanent. They are part of an ongoing, evolving drama, and we are fortunate enough to have a front-row seat to witness this chapter of change. The shrinking of this iconic storm is a humbling reminder that the universe is in a constant state of flux, and that our understanding must evolve just as quickly as the cosmic phenomena we strive to comprehend. After exploring the shrinking storm on Jupiter and the topsy-turvy day on Venus, we travel to the solar system's outer darkness, where two worlds hold a secret more dazzling than any gemstone. We often picture diamonds as rare, precious stones forged deep within Earth over billions of years, brought to the surface by violent volcanic eruptions. But on the ice giants Neptune and Uranus, this process is not a slow geological marvel, it's a constant, dramatic weather event. The 25th surprising truth is that it literally rains diamonds deep within their atmospheres. This isn't science fiction or metaphor. It is a serious scientific hypothesis that turns the fantastical idea of diamond planets into a plausible, ongoing phenomenon. To understand how such an incredible thing is possible, we need to venture into the hellish conditions that define these distant worlds. Neptune and Uranus are classified as ice giants, but don't let the name fool you into thinking they are just frozen balls of ice. Their interiors are realms of extreme pressure and temperature that defy human comprehension. Far below their outer cloud decks of hydrogen, helium, and methane, the pressure becomes so immense, millions of times greater than the atmospheric pressure on Earth, that it fundamentally alters the nature of matter itself. The planet's atmospheres are rich in methane, a molecule composed of one carbon atom bonded to 4 hydrogen atoms. In this crushing, high-temperature environment, the incredible forces are enough to rip the methane molecules apart, squeezing the hydrogen atoms away and leaving behind free-floating carbon atoms. These lone carbon atoms, the very same element that forms coal and graphite in less extreme settings, are then subjected to the ultimate planetary pressure cooker. Under these conditions, the carbon atoms are forced into the rigid, crystalline structure of diamond. It's a process of alchemy driven not by magic, but by the unforgiving laws of physics. Now envision the scene. Deep within the slushy, fluid interior of Neptune, countless microscopic diamond crystals begin to form, condensing out of the soupy mixture of compressed gases and ices. As these tiny diamonds grow, they begin to fall. Given their immense density compared to the surrounding material, they sink, pulled by the planet's powerful gravity toward the core. Scientists hypothesize that these aren't just tiny specks of dust. They could grow into diamond hailstones, perhaps even reaching the size of pebbles or larger, creating a continuous shower of solid gemstones falling through the alien interior. Imagine a landscape of unimaginable pressure where the sky is not made of gas but of a thick, hot fluid, and where the precipitation is not water but a glittering, hard rain of diamonds sinking endlessly toward a mysterious core. This proposed diamond rain is more than just a poetic idea. It could play a crucial role in the internal dynamics of these planets. As the dense diamonds plummet downward, they release gravitational energy, which is converted into heat. This process could help explain a long-standing mystery: why the interiors of these ice giants are so much hotter than models predict. The continuous sinking of this diamond hail may be acting as an internal engine, generating warmth that churns the planet's interiors and influences their bizarre magnetic fields, which are tilted and offset from the planet's centers. While we cannot yet send a probe deep into Neptune's atmosphere to collect a sample of this diamond rain, scientists have found ingenious ways to test the hypothesis here on Earth. Using powerful high-energy lasers or devices called diamond anvil cells, researchers can recreate a tiny slice of the conditions found inside these ice giants. In one famous experiment at the SLAC National Accelerator Laboratory, scientists took a plastic film similar in composition to methane and hit it with the intense shock waves generated by an optical laser. This simulated the immense pressure and heat of Neptune's interior. Using X-ray pulses, they were then able to watch the chemical reaction in near real time. They observed that the carbon atoms from the plastic did, in fact, rapidly compress into tiny diamond structures. This provided the first direct experimental evidence that diamond rain is not just a theoretical fantasy, but a plausible physical process. The experiment suggested that the diamonds forming on Neptune and Uranus could be much larger than previously thought, potentially creating a vast layer of diamond-rich material around the core. Some theories even speculate that under the even more extreme pressures at the very center of these planets, the diamonds might not remain solid, but could melt into an exotic liquid diamond ocean, a concept that stretches the imagination even further. So the next time you look at a diamond ring or pendant, consider its extraordinary cosmic journey. On Earth, it is a symbol of eternity formed over eons. But on distant, blue-hued worlds at the edge of our solar system, its chemical twin is a common ingredient in a perpetual, spectacular storm. This truth transforms these remote ice giants from simple points of light in a telescope into worlds of dynamic, almost mythical, internal violence and beauty. They are natural laboratories for extreme chemistry, showing us that the universe is capable of creating wonders that surpass our wildest dreams, where the most sought-after gem on our planet is merely another form of weather in the cosmic forecast. As stable and permanent as our night sky may seem, with the moon faithfully orbiting our world in a seemingly eternal dance, this celestial partnership is undergoing a slow but relentless change. The moon is not fixed in its place. It is in the process of leaving us, drifting further into space year after year. This gradual retreat happens at a rate of about 1.5 inches or 3.8 centimeters annually. While that might sound negligible on human timescales over the epic span of cosmic history, this tiny annual shift adds up to a dramatic transformation of the Earth-Moon system, revealing that even the most fundamental aspects of our celestial neighborhood are in a state of constant, graceful flux. The engine driving this cosmic separation is the same force that creates the rhythmic rise and fall of our ocean tides, gravity. The moon's gravitational pull doesn't affect the entire Earth uniformly. It tugs most strongly on the side of our planet facing the moon, pulling the ocean slightly toward it and creating a bulge of water we know as the high tide. But there's also a second, equally important tidal bulge on the exact opposite side of the Earth. This occurs because the moon's gravity pulls the solid body of the Earth away from the water on the far side, or conversely, because the rotational force of the spinning Earth flings the water outward. The result is a planet that is subtly stretched, with two oceanic bulges, one facing the moon and one directly opposite. Now, here is where the magic of orbital mechanics comes into play. The Earth rotates on its axis much faster than the moon orbits around us. Our planet completes a full spin every 24 hours, while the moon takes about 27 days to complete its circuit. This means the Earth is constantly spinning through these two tidal bulges. The friction between the rotating Earth and these moving water mounds acts as a brake, very slowly but surely slowing down our planet's rotation. This transfer of energy has to go somewhere, and it follows a fundamental law of physics, the conservation of angular momentum. As the Earth loses rotational energy, that energy is transferred to the moon, giving it a slight boost. This extra energy doesn't make the moon move faster. Instead, it pushes the moon into a slightly higher and therefore more distant orbit. It's a beautiful, intricate trade. Earth's spin is gradually slowing down, lengthening our days, and in exchange, the moon is granted a one-way ticket to a more distant future. To visualize this, imagine an ice skater performing a spin. When she pulls her arms in close to her body, she spins faster. When she extends her arms outward, her spin slows down. In our Earth-Moon system, the Earth is the skater, and the moving tidal bulges are like her, slowly, constantly extending her arms. This action transfers momentum outward, slowing her spin and pushing the moon, the beneficiary of that energy, further away. This process will continue until the Earth's rotation slows to match the moon's orbital period, a state known as tidal locking. If this were to ever fully occur, a single day on Earth would last as long as a full lunar month, and the moon would only be visible from one hemisphere of our planet. Fortunately, this ultimate fate lies billions of years in the future, far beyond the lifetime of our sun. Understanding this slow drift allows us to rewind the cosmic clock and peer into a dramatically different past. Since the moon is receding now, it must have been closer to Earth in the ancient past. Hundreds of millions of years ago, the moon would have appeared significantly larger and brighter in the sky. This closer proximity also meant its gravitational influence was stronger, creating much more extreme tides that swept across the continents. Furthermore, because the Earth was spinning faster to conserve the total angular momentum of the system, the days were considerably shorter. A day in the age of the dinosaurs, for instance, may have been only about 23 hours long. This also had a stunning effect on one of nature's most spectacular events, the total solar eclipse. With the moon closer to Earth, its apparent size in the sky was larger. This meant that when it passed in front of the sun, it was far more likely to completely obscure the solar disk, creating the breathtaking diamond ring effect of a total eclipse. In that era, total solar eclipses were a much more common and widespread phenomenon. As the moon continues its retreat, there will come a time in the distant future when it will appear too small in our sky to ever completely cover the sun, and total solar eclipses will become a memory of Earth's geological past, a ghostly echo of a time when our companion in space was a much more intimate part of our world. After exploring the dynamic retreat of our moon and the diamond reigns of the outer planets, we journey to the grandest scales of the cosmos, where we find not an abundance of matter, but a staggering, almost unimaginable emptiness. In the northern constellation of Boötes, the herdsman, lies one of the universe's most profound and unsettling mysteries, the Boötes Void, a spherical region of space so vast and so empty it has earned the nickname the Great Nothing. Stretching an astonishing 330 million light-years across, this void is a cavern in space so colossal that if our own Milky Way galaxy were placed at its center, we would have been utterly alone, adrift in a sea of darkness, with no knowledge of any other galaxies until well into the 1960s. To truly grasp the scale of this emptiness, let's first consider what a normal, rich region of space looks like. In our own cosmic neighborhood, galaxies are gathered into groups and clusters. Our Milky Way is part of the local group, which contains a few dozen galaxies. These groups are then strung together along vast, intricate filaments, forming a cosmic web that stretches across the universe. In these dense filaments, you might find thousands of galaxies within a span of just a few million light-years. Now, imagine all of that simply vanishing. The Boötes Void is a spherical bubble in this web, a hole in the cosmic cheese where the filaments seem to part ways and leave behind a breathtakingly empty volume. While it's not a perfect vacuum, astronomers have identified a handful of galaxies drifting in this immense darkness. Their number is shockingly small. Instead of the thousands or even tens of thousands of galaxies you would expect to find in a region of that size, surveys have found only about 60. The space between these lonely islands is a gulf of profound isolation, a silence that spans distances almost too large for the human mind to comprehend. The existence of such a tremendous void presents a significant challenge for our models of cosmic evolution. The prevailing theory of the universe's large-scale structure, driven by the subtle fluctuations in the ancient cosmic microwave background, predicts that matter should clump together in a web-like pattern. While this model allows for voids to form, the sheer scale of the Boötes Void pushes the limits of what is considered statistically plausible. It is so large that it's difficult to explain through standard gravitational collapse alone. Some scientists have proposed that it could be the result of multiple smaller voids merging together over billions of years. Others have entertained more exotic ideas, such as it being the imprint of an encounter with a parallel universe in the multiverse, though this remains highly speculative. The void forces cosmologists to re-examine their assumptions and refine their simulations, a reminder that the universe often has surprises that defy our neatest theoretical boxes. To experience the sheer awe of this structure, picture a dramatic journey through the cosmos. We begin by flying at an incredible speed through a supercluster, where galaxies of all shapes and sizes whip by in a blur of brilliant light spirals like spinning pinwheels, ellipticals like golden orbs, all packed relatively close together. The space around us is vibrant and crowded, a metropolis of stars. Then, without warning, the galaxies begin to thin out. They become fewer and farther between, like the last scattered towns on the edge of a great desert. And then we cross the threshold. Suddenly, there is nothing. We are adrift in the Boötes Void. The vibrant cosmic city is gone, replaced by an endless, dark, and nearly featureless expanse. In every direction, the view is the same, an overwhelming blackness punctuated only by the faint, rare gleam of one of the void's lonely galaxy inhabitants, shining like a solitary lighthouse in the most immense ocean imaginable. The sense of scale and isolation in such a place would be utterly humbling, a visceral understanding that the universe is not a uniform sea of matter, but a tapestry of breathtaking extremes woven with threads of brilliant light and patches of profound, silent nothing. We often see our planet depicted as a perfect, beautiful blue marble, a sphere suspended in the blackness of space. It's an image that feels intuitively correct, a symbol of cosmic harmony and completeness. But this 28th surprising truth reveals that our world's shape is not so geometrically pure. The Earth is not a perfect sphere. Its daily rotation has sculpted it into what is known as an oblate spheroid, a shape that bulges outward around its middle and is flattened at its top and bottom. This means that if you were to measure the planet's diameter from one point on the equator to the exact opposite point, you would get a number about 26.5 miles or 43 kilometers, larger than if you measured from the North Pole to the South Pole. While this difference might seem negligible on a globe 12,742 kilometers across, it is anything but trivial. It is a fundamental feature that dictates everything from the path of satellites to the very flow of our oceans. The force responsible for this bulging is the same one you feel when you take a sharp turn in a car: centrifugal force, a consequence of the Earth's rapid spin. Imagine our planet as a ball of soft, pliable clay spinning on a potter's wheel. As it rotates, the material at the equator, farthest from the axis of spin, wants to fly outward, while the material at the poles, right on the axis, experiences almost no such push. Over billions of years, this constant, gentle tug has caused the Earth to settle into its current, slightly squashed shape. The equatorial bulge means that the highest point on Earth is not, as you might assume, the summit of Mount Everest. While Everest is the highest mountain above sea level, the point on the Earth's surface that is farthest from the planet's center is actually the peak of Mount Chimborazo in Ecuador. Because Ecuador sits right on the equatorial bulge, Chimborazo benefits from this extra lift, making its summit over 2,100 meters farther from the Earth's core than Everest's peak. This deviation from a perfect sphere is not just a curious geographical footnote. It is absolutely critical for the functioning of our modern technological world, particularly for the global positioning system that guides our cars and phones. GPS relies on a fleet of satellites orbiting the Earth with incredible precision. For these satellites to calculate a location on the surface to within a few meters, their orbital paths must be predicted with astonishing accuracy. This requires a near-perfect model of the Earth's gravitational field, and because the Earth is an oblate spheroid, its gravity is not uniform. The extra mass concentrated in the equatorial bulge creates a slightly stronger gravitational pull around the middle of the planet. This uneven gravity tugs on the satellites in complex ways, causing their orbits to slowly precess or wobble over time. If the system's computers used a simple spherical model of the Earth, these orbital perturbations would not be accounted for, and the resulting positional errors would accumulate at a rate of several miles per day, rendering the entire system useless. Therefore, the mathematical model used by GPS incorporates the precise dimensions of the oblate spheroid, allowing engineers to predict and correct for these gravitational nudges and deliver the pinpoint accuracy we take for granted. The planet's shape also has a profound influence on our climate and weather patterns. The bulge at the equator means that this region is closer to the Sun and receives more direct solar energy than the poles. This uneven heating is the primary engine for the Earth's entire atmospheric circulation system. The warm, moist air at the equator rises, creating a band of low pressure, while the cooler, denser air at the poles sinks. This temperature difference, amplified by the planet's rotation, drives the trade winds, the jet streams, and the massive ocean currents that distribute heat around the globe. If the Earth were a perfect sphere, these climatic systems would be vastly different, and the world as we know it would be a much more extreme and likely less hospitable place. The oblate shape, therefore, is not a static geological fact. It is a dynamic force that actively participates in sculpting the environment we live in, a constant reminder that the very form of our world is in a dialogue with the forces that move upon it. This truth connects the grand, physical fact of our planet's rotation directly to the weather outside your window and the reliability of the map on your screen. Yet, as stable and permanent as Earth's shape may be, the universe enforces one constant that is absolute and unbreakable for all of us, no matter where we are. Just as a highway has a maximum speed that no car can legally exceed, the cosmos has its own ultimate speed limit, a universal rule that is woven into the very fabric of reality. This 29th surprising truth is that the speed of light in a vacuum, a staggering 186,000 miles per second, is the maximum possible velocity for anything in the universe. This isn't just a property of light, it is a fundamental cap on causality itself, a rule that ensures the past always comes before the future and that cause always precedes effect. To understand why this speed is so special, we need to look at the brilliant work of Albert Einstein. His theory of special relativity revealed that this cosmic speed limit isn't just a barrier, it's a fundamental feature of the relationship between space, time, mass, and energy. The key insight is that as any object with mass moves faster and faster, its mass doesn't stay the same. From the perspective of a stationary observer, the object's mass actually increases. This effect is negligible at the speeds we encounter in daily life, a car, a plane, even a rocket. But as you approach the speed of light, this mass increase becomes dramatic. The closer you get to light speed, the more massive you become, and therefore the more energy is required to accelerate you even a tiny bit more. To actually reach the speed of light, an object with mass would require an infinite amount of energy. Its mass would balloon toward infinity, making further acceleration not just difficult but mathematically impossible. This is why nothing with mass can ever achieve, let alone surpass, this ultimate velocity. The universe has a built-in regulatory system that prevents it from happening. We can see this principle in action in our largest and most powerful scientific instruments, particle accelerators like the Large Hadron Collider. In these colossal underground rings, physicists accelerate tiny subatomic particles like protons to incredible speeds. They can get these protons to 99.9999991% of the speed of light. But that last fraction of a percent, that final push to reach 100%, is where the cosmic rule truly asserts itself. To get from 99.9% to 99.99% of light speed requires a massive injection of energy. And to go from 99.999% to 99.9999% requires an even more colossal amount, far out of proportion to the tiny speed gain. The graph of energy required versus velocity isn't a straight line. It's a curve that shoots up toward infinity as it approaches the speed of light. The particle accelerator uses enough electricity to power a small city just to make these tiny, final adjustments, providing a tangible, experimental proof that the universe does not allow its speed limit to be broken. This universal constant does much more than just govern motion. It defines the very structure of cause and effect, creating what physicists call light cones that dictate what events in the universe can possibly influence each other. Imagine a single event like the flash of a light bulb turning on. The light from that bulb spreads out in all directions at the speed of light, forming an expanding sphere. This sphere defines the future light cone of that event, the region of space-time that can be influenced by the bulb being turned on. Any event outside of that expanding sphere cannot know that the bulb has been turned on yet because the information traveling at the speed of light hasn't had time to reach it. This ensures that no signal, no influence, and no information can travel faster than light. If something could, it would be possible for an effect to happen before its cause in some reference frames, leading to logical paradoxes, like being able to send a message back in time to prevent your own birth. The fixed, finite speed of light acts as the ultimate guardian of cosmic logic, preserving a coherent and ordered universe where the past, present, and future remain in their proper sequence for all observers. And now we arrive at our final, 30th surprising truth, one that grants our current moment in the vast sweep of cosmic time a profound and bittersweet significance. We are living in the absolute best time in the entire history of the universe to be an observer. This isn't just a feel-good statement, it's a direct consequence of the accelerating expansion we explored earlier, a fact that bestows upon our civilization a fleeting, golden age of cosmic visibility that will never come again. Future astronomers, no matter how advanced their technology becomes, will inherit a night sky that is fundamentally impoverished, a lonely vista from which the grandest chapters of the cosmic story have been irrevocably erased. The culprit, once again, is dark energy. That mysterious force is not only pushing galaxies apart, but as space stretches, it also stretches the very light traveling through it, shifting it to longer, redder wavelengths in a process called redshift. For now, the light from countless distant galaxies is still able to reach us, their photons having journeyed for billions of years to finally tickle the mirrors of our telescopes. We can see the universe in its rich, adolescent structure, teeming with galaxies in every direction we look. We can even detect the faint, ancient whisper of the cosmic microwave background, the afterglow of the Big Bang itself. We are like spectators who have arrived at a theater just as the curtain is rising on the entire cosmic drama, able to see both the opening act and the sprawling set that fills the stage. But the play is not over, and the stage itself is expanding, pushing the actors further and further into the wings. As dark energy continues its work, galaxies beyond our own local gravitational family will be carried away by the flow of space itself. Their light, already redshifted, will be stretched further and further, shifting from visible light to infrared, then to microwaves, and finally into faint radio waves, their energy dissipating into an undetectable whisper. The wavelengths will become so long that they can no longer be distinguished from the general background noise of the universe. From the perspective of a future astronomer on Earth, those galaxies won't just be far away, they will have effectively vanished. Their light will have been redshifted into oblivion, carrying its information beyond the cosmic horizon, a point of no return beyond which no signal can ever reach us. Imagine a poignant visual timeline of the cosmos, stretching from the Big Bang to a future trillions of years from now. In our current era, the timeline is ablaze with points of light, a glittering tapestry of galaxies crowding the frame. But as the timeline extends forward, a darkness begins to creep in from the edges. First, the most distant and faint galaxies wink out one by one, their light stretched beyond detection. Then whole clusters of galaxies fade from view, leaving only the members of our own local group, Andromeda, the Triangulum Galaxy, and a few dozen smaller dwarfs still gravitationally bound to us. Eventually, even these nearby companions will have merged with the Milky Way, forming a single, giant elliptical galaxy that future inhabitants might simply call home. The sky, which once held 100 billion galaxies, will contain only one. The cosmic background radiation, the last echo of the Big Bang, will have redshifted so dramatically that its wavelength will be larger than the observable universe itself, rendering it completely undetectable. Any civilization that arises in that far future epoch will look out upon a black, nearly empty void with no evidence of an expanding universe, no clue about the Big Bang, and no conception of the vast cosmic web that we are privileged to see today. Their universe will be an island in the darkness, and the greatest story ever told will be one they can never read. This makes our current age of discovery, the last few hundred years in a cosmos 13.8 billion years old, a phenomenally special and transient window. We exist in a sweet spot, long enough after the Big Bang for complex elements and planets to form, and life to evolve to consciousness, but early enough that the universe hasn't yet expanded into permanent isolation. We have just developed the tools to peer back to the very beginning of time and map the large-scale structure of everything, and we are doing so at the precise moment when that structure is still visible. This truth elevates every image from the Hubble and James Webb Space Telescopes from mere beautiful pictures to cosmic artifacts, precious snapshots of a universe in its prime, a view that is destined to fade. Our curiosity is perfectly timed, granting us a front-row seat to the grandest show in the cosmos, a performance that is already beginning its final act. It's a humbling and inspiring thought that we, here and now, are the universe's eyes upon itself, able to witness its full glory before the curtain of expanding space falls, leaving only a memory of the light. And so we reach the end of our voyage through 30 cosmic revelations, a journey that has taken us from the quantum foam shimmering beneath reality to the cold, expanding horizon of our observable future. We began by shattering the very idea of a center, learning that we are not at the heart of anything, but are instead adrift in a centerless, expanding whole. We then discovered that the world we see is a mere 5% sliver of the true cosmos, overshadowed by the invisible, gravitational grip of dark matter and the repulsive push of dark energy. We saw that space and time are not a static stage but a flexible fabric that bends around mass and ripples with gravitational waves, and that time itself is a personal, malleable experience, flowing at different rates throughout the universe. We peeled back the illusion of solidity to find that we are all, quite literally, made of nothing vast, empty atoms held together by forceful interactions. We even dared to consider that every choice spawns a new universe in an infinite multiverse, and that the fundamental laws of physics might not be constant at all, but slowly drifting over cosmic eons. Each of these truths on its own is a mind-altering shift in perspective, but taken together, they form a radical new portrait of existence. They reveal a universe that is not the cold, clockwork mechanism of classical physics, but a vibrant, dynamic, and deeply strange reality where the impossible is routine and common sense is a local phenomenon, useful only within the narrow confines of our daily lives. This is a cosmos where black holes glow and evaporate, where diamonds rain down on distant worlds, and where the past, present, and future may all exist simultaneously in a timeless block. It is a realm where the act of observation seems to conjure reality into being, and where the vacuum of space itself seethes with unimaginable energy. The serene, stable night sky is a grand illusion, masking a universe of constant, violent, and beautiful transformation. This grand tapestry of discovery is both profoundly humbling and incredibly inspiring. It humbles us by constantly reminding us of our scale, not just our physical smallness on a pale blue dot, but the limitations of our innate intuition. Our brains evolved to navigate a world of medium-sized objects moving at modest speeds, and they are simply not wired to intuitively grasp the counterintuitive rules that govern the very small, the very fast, and the very large. Every time we push the boundaries of knowledge, the universe reveals another layer of mystery, reminding us that for every question we answer, a dozen more, even more profound, take its place. We are like explorers who have just landed on the shore of an infinite ocean, only now beginning to comprehend its vastness and its depths. Yet, this is also what makes the human endeavor of science so inspiring. With nothing but curiosity, reason, and ingenuity, we have managed to decode the life cycles of stars, listen to the echoes of spacetime itself, and look back to the very first light of creation. We have discovered that we are made of stardust, permanent records of ancient cosmic furnaces. We are the universe's way of becoming aware of itself, a fleeting moment of consciousness in which the cosmos can look upon its own grandeur and wonder at its own origins. The fact that we can uncover these truths, that we can even formulate the questions, is a testament to a profound and beautiful connection between our minds and the cosmos they seek to understand. As this journey concludes, we are left not with final answers, but with a renewed sense of wonder and an invitation to keep looking up and asking questions. The exploration is far from over. In many ways, it has just begun. The mysteries of dark matter and dark energy, the quest for a theory of quantum gravity, and the ultimate fate of our universe are the great frontiers waiting for the next generation of thinkers and dreamers. So we turn the conversation over to you. Which of these 30 truths reshaped your understanding of reality the most? Was it the centerless expansion, the holographic universe, or the realization that you are living in a privileged cosmic moment for observation? Share your thoughts in the comments below. We are genuinely excited to hear which concept sparked that sense of awe for you. If you enjoyed this voyage to the edges of understanding, please give the video a like, as it helps us continue creating journeys like this one. And of course, subscribe to the channel so you don't miss our next exploration into the wonders of space, physics, and the incredible universe we call home. The cosmos is strange, beautiful, and waiting to be discovered.